Oh, brilliant.
Can you use that one?
Check, check. 1, 2. Hey, hey. Check, check. 1, 2. Hey, hey.
one's on now. You want to use that. And I'll do that. Once the 10 minutes is up, I'll put the other slide up.
You'll notice when we split up. Yeah. All right, let's get started. So thanks for joining this community discussion on systems biology, community needs, plans, and visions. So we will try to keep this rather relaxed and have a discussion. Like first I will kind of set the theme of the discussion, and then we'll probably split it up into different groups such that you can discuss your needs and visions in smaller groups. And then we will wrap it up in the last like 10 minutes or something, and every group can present what their ideas were. So one thing to note is this session is being recorded. We did not quite expect this from the beginning, so if anybody wants to, like, it's just important that you are aware of this. Also, yeah, one announcement or two announcements maybe. Are that we want to organize SysBio community calls following this meeting and this conference. So here's the QR code where you can provide your email address to stay up to date with that. Then also, for those who are not aware, we have a SciML Slack channel, so you can follow that on the Julia Slack. And finally, we are organizing a systems biology community meetup with pizza later tonight at 6 p.m. in room 32G 4451. All right, so in systems biology, I think today we face several big challenges. It's tricky to define a model, come up with the right model. It's tricky to estimate the parameters of this model. And it's also, quite often you don't get the goodness of fit that you're hoping for, and then you need to further refine the model. And I've seen with several people in this room, like a diverse audience, and people are working across this whole spectrum. And when it comes to model definition, for instance, I would like to introduce Carlos over there, who is working in multi-scale modeling and has developed also a framework for rule-based modeling. Carlos, do you want to say a few words about yourself?
Carlos, I'm from Alpha Labs, and this is what I've been working on much of my life.
Thanks, Carlos. Also, Torkel, I think, key developer of Catalyst. Do you want to say a few things on model specification, Catalyst?
Catalyst is just a chemical reaction and forms of differential equation. Partially just with all kinds of chemical reaction methods.
Yeah, definitely a very useful tool in Julia for specifying biochemical reaction networks. Yeah, for parameter estimation, there are obviously also a lot of different tools. A new one that has just been recently developed is ptab.jl, developed by Sebastian Persson, for instance. Do you want to say a few words?
Yeah, I'm a PhD student at the University of Gothenburg, and I work a lot with the inverse problem, or the models and how to make them as efficient as possible.
All right, yeah, and obviously, if you don't get the goodness of fit, then you try to do something with universal differential equations. And Nino will give a talk later today. Do you want to give a brief introduction?
Hi, I'm Nina. I'm from hackathon in Bonn, and this is something new that we're investigating, and it's quite exciting.
All right. Yeah, so these major challenges are partially addressed already in Julia, and I think we are on a good way there, and it would make sense to bring the community together to actually figure out, okay, what are the key pain points, and where can we collaborate to create a better, even better open source ecosystem for systems biology tools. And just to get a bit of a feel of the audience, because we will split it up into discussions later, we've prepared a few questions. So look around what people say, and then maybe you can use this information to self-organize into groups of roughly 5 people. Elizabeth?
Hi, I'm Elizabeth. I'm a colleague of Paul's. We have a few questions, and if you could just raise your hand answering, that would be amazing. So the first question is this your first JuliaCon? So for whom is this the first? Oh, nice. So it's the first in-person JuliaCon? You attended video before? Yeah, okay. Have you co-developed a Julia package before? Nice, okay. And the other people, I assume you more see yourself as users, I would assume. Nice. Have you applied a Julia package for biological research? So I think, yeah. Are you using Julia for machine learning? Oh, you've done that? Cool. Are you using Julia for mechanistic modeling? Okay. Are you currently working in industry? Oh yeah, so it seems pretty much 50-50 industry, academia. Okay, cool. So maybe you've seen a little bit, yeah, I mean, we want these questions also to motivate kind of who of the people we introduced before, like who you feel most connected to.
I was actually wondering, can I get a photo of everyone who has a hand up saying it's their first JuliaCon?
Yeah. Okay, is this your first JuliaCon?
First JuliaCon.
Oh, that's really nice. I didn't expect that, huh?
Yeah.
Oh, it's not one.
All right, thank you. I think that's just a really cool fact. I didn't expect that.
Yeah, me neither. Me neither. Okay. Do you want to continue?
Sure. Yeah, so I already announced the plan for today. This was kind of the introduction. Took about 10 minutes, I guess. And now the good thing would be if you could split up in groups of 4 or 5, something like this, and discuss the points that will be on the next slide. As a rough guideline, you can discuss anything you want, and we will walk around and try to moderate the discussion a little bit in the meanwhile. And then when the session comes to an end, in the last 15 minutes, we want to bring the group, like have one of every group coming out at the whiteboard and briefly explain, give a short summary of what they've been discussing and potentially what plans might emerge from this. So with that, let me introduce the suggested discussion points. Like I said, feel free to discuss anything else if you want. So the first one would probably be, well, I guess introduce yourself to your colleagues in the discussion group, and then as part of that, probably explain what you think are your needs, plans, and visions. Then as a second point, you can discuss which existing systems biology tools hold great potential for faster implementations if ported to Julia. So you might have experience with software that's not in Julia, but that would be nice to have in Julia. Then the third point would be which new tools are enabled by the features of the SciML ecosystem. So there's obviously always progress, new tools are being developed, and this is more a question of what could be the next step. And then also discuss where you can find synergies and common interests for joining efforts on systems biology tool development within your group. Not necessarily only tool development, but synergies for use of tool and development that goes hand in hand. And finally, how can we improve the existing communication channels to facilitate coordinated and collaborative tool development? You see, again, the QR code for the SysBio community call sign up, where you can leave your email address, and we'll try to organize and bring the community together more regularly. This is one way of facilitating communication, but if you come up with other ways, please share this at the end of the session. So with that, I encourage you to split up into groups of 5, and ideally not with your coworkers. So
maybe distribute on tables. Maybe Sebastian, you can take this table. Nina, the one over there. Toko. Not you. The other.
you want to, let's see. Hello, test. This one's on too, so if you or whoever's using the whiteboard wants to explain, then everyone can do it. Yeah, okay. And then the next event, does it start in here immediately, or is there a break after?
Ooh, I don't know. I'm sorry. So what is on your schedule?
I'm here until 4 o'clock.
Okay, but what does the schedule say for you?
Well, they gave me a piece of paper, but they didn't give me the full one. So
Okay.
it just says,
So you don't know when the next one starts?
no, maybe the board's having it. The next one does start.
Does the microphone work? All right, so we have to wrap this up now. We don't have too much time for every group, 2 minutes. So you can continue the discussion at the SysBio community meetup later over pizza. So yeah, I'm asking probably the first group over there to share their results and their main discussion points. And please use the microphone so that people online can hear you.
Okay, hello. We were a group that's quite heterogeneous, but it's all what was about modeling, and we had basically 2 pinch points. One was documentation and structure of the whole ecosystem, so in particular optimization frameworks, inverse problem solutions. There's quite a few packages that we can use to do that, and it's not quite clear for somebody coming into it what is the best to use. So documentation, I think, as a map or best practice guides would be useful. And the other big point that we discussed was composability and interaction between models, which also addresses the consistency checks for models, maybe units, including in ModelingToolkit. And we can define models in units, and if models are using incompatible units, then transform the units transparently. I think that's an important thing, so kilomoles and moles transitions. Rules-based modeling was a missing point, I think, that we found, that there's no package to do that consistently. And, well, one question that we couldn't find the answer in, will ModelingToolkit, for example, when JuliaSim comes in, continue to be full-featured, or will there be features within ModelingToolkit that will be on the paid tier? So I think that's an important question to address as well. I hope I didn't forget anything. Okay, thank you.
Thank you very much. Maybe if somebody wants to come out from the second table and explain the results. No. Yeah, like this table in front here. Yep. All right, sure. Let's take the table over there in the back. You need to take notes then.
Oh, okay. So we had a fairly diverse group of folks who were doing different things. One of the things that common motif that came up was it would be nice to have the ability to wrap more existing packages. This came up in RNA-seq, doing kind of like wrapping the existing Python and R packages in like downstream analysis of RNA-seq would be helpful to have it just be plug and play, right, to do that kind of research. Similarly, we have someone from Genelia, so image analysis came up, and so interacting with tools like ImageJ, like standard industry tools that maybe biologists are more familiar with, is an important thing. What we spend most of the time talking about was actually error messages and how to make those interactive perhaps, or different order of the stack trace came up. And so we found it was an interesting idea. We didn't have potentially groundbreaking proposals, but we're curious to see how the this premise of Julia, one of the main advantages is that you can drop down in, right, anywhere in the stack, and it's all Julia all the way down, right? Whereas so much of bioinformatics and biological tools are you hit the sea level and then, it's a bigger project to debug after that. So it'll be interesting to see how those, what may be kind of cryptic error messages now might not be so cryptic once adoption has increased and people are more fluent and, I can actually drop into that level and see what's going on. This is more of an adventure than a challenge to understanding. So that's where we are.
Yeah, thanks a lot. I think this is a very useful points, very useful feedback. Does anybody from this table want to present their results, or? Thanks, James.
Yeah, sure. So I think a lot of similar themes in our discussions. Let's see, kind of starting out, a couple of the things that we were mentioning. One main thing is more kind of automated methods for composing models, and specifically, like, one of the main things that I run into myself when we were discussing is that models that are being defined in SBML could have a number of different annotations for various proteins, phosphorylation sites, anything you could think of that modifies the protein. So, in Julia, could we have different ways to, have databases of kind of standardized annotation potentially? Or, if we think about kind of going a little more kind of out there than that, like, could potentially, there be some packages that involve language models that could take in some SBML model with a specific annotation, and then maybe look in the literature to see kind of what that other, if there's any other standardized annotations, if there's other relations to the literature that could be useful in figuring out what is in the model you're working with. A couple other things that came up, like units was one that we came up with as well, and I heard in other discussions, and kind of making just the unit handling more transparent across the different packages within Julia. And then maybe also, if there are discrepancies with other packages in other languages, maybe the Julia packages could have kind of explicit comparisons to other packages that are more widely used to adopt kind of more users into the Julia ecosystem. Let's see. I think one thing that also came up was image analysis functionality as well. So having ways in Julia to take in microscopy data. We were discussing kind of legacy tools like ImageJ, et cetera. Having equivalents in Julia that could easily and efficiently read in data and create systems to simulate all within the Julia ecosystem would be nice. I guess another main theme was just getting tools that are more easily used for the general biologist that isn't necessarily, as well versed in programming and might be a little scared when they take a look at a neural ODE package or a symbolic regression package. Kind of having as many of these packages streamlined and kind of linked together and providing, interpretable results for a biology user could, eventually, expand the adoption of the Julia language in the space. Let's see. Those are some of the main things. Anything else that I missed? Okay. All right. I will stop there then. Thank you.
Brilliant, thanks. So from the table at the front here, I think the person who was about to share the results is not yet here, or is he? Ah, oh there. Yes, Harry, go ahead.
I apologise for repeating what everyone else has said.
You need that? Yeah, thanks.
Well, I don't need. Do I need this? Or?
You need it for the people.
Oh, bless
in
them.
the live stream.
Yeah, I think we, I assume, said many similar things, and I think if we're in the interest of progressing forward, probably need to improve adaptability from kind of subject experts. So while there's massive improvements all the time in features and there's new algorithms and new methods, and it's brilliant because we all understand it, the adoption by subject experts who aren't keeping up to date with the features that are coming out, they probably are getting lost on this. So does there need to be kind of a slowdown on feature development and maybe a push on kind of user interfaces such that you can get this pipeline and show subject experts, okay, we can work through this step, and this step, and this is how you can do that. Because I think the features are still, unless somebody said something different, I don't think there's many features that are drastically lacking in terms of optimization, sensitivity, identifiability, all these things. But what is to some degree lacking is this idea of, okay, start to finish, how can you do that within kind of a single workflow that is usable and interpretable for these subject experts? Did I miss anything else? I think also, to a degree, I think we mentioned multi-scale modelling and looking to try and improve the connectivity between different ones, because as we just mentioned over there, there's lots of different models that do essentially the same thing, but how do you combine them to create more advanced, more interpretable models if you've got, because they're all a bit standalone, you've got PDE camp, CFD camp, 0D camp, and there doesn't appear to be much interaction in kind of joining all those things up. Did I miss anything? Okay, thanks, boss. Cheers.
Thank you.
Yeah, thanks to everyone participating in this discussion and sharing their thoughts. I think we've talked. You wanted to say something? Yeah, a very short one.
So I'm curious to know, because you're both from Julia organizing this, what kind of systems biologies are you working at Julia Hub? So like what work have been done there as a part of the community?
So the work that we are doing essentially is we develop an optimization tool that is called Pumas QSP. And so we're not developing models ourselves, but what we are doing is we help clients to use our optimization tool on their models. So this is the part this is the systems biology part that we are actively working on. Yeah?
What I said earlier, how much of the development that goes into what's done in Julia Hub, it goes into Julia Sim and Pumas, how much of that will be available for the academic community without being part of that phase here?
Yeah, I think Elizabeth can answer this question. Can you also repeat the question for the listeners online?
So for academics who want to use, for example, Pumas QSP, it's completely free. You sign up and you can use it.
So
Yes, yes. So there are local options, so they are really completely free. If you use our cloud options, you have to pay for the usage of the cloud, but not for the software. Yes, but if you don't want that, you can just use the local version. We very much encourage people to try it out. So if you're academic and you're curious, just have a look.
All right, yeah. So I think for the future, we'll try to create a short document, wrap up the main points here, shared with the community as a kind of common basis, such that it's transparent what are the pain points there. And I would hope that next JuliaCon, we might see some of those already resolved. And I encourage everybody to continue the discussion tonight over pizza and potentially tomorrow when we have the mini symposium. And of course over the whole conference as well, and connect with the people that you've chatted with over the last hour. Thank you very much.
Yeah?
I was just thinking for the volunteer channel Slack that we're post-lunch and go over after the picture.
Sorry, say again?
So I'm just seeing on Slack in the volunteer channel, there's proposed lunch for people interested in biology. So,
At what day? On what day?
Today. It's for like
nice.
Julia, so if you're it's
Yeah.
less systems biology, more like bioinformatics interested folks.
Yeah,
But we're
nice.
just gonna go meet at the big table at Clover, which is just up the
Perfect.
road, and delicious vegetarian food. So
Nice.
yeah, please join us.
So lunch and dinner sorted.
Well, we're not paying for anything. Just to be clear. Bring your own clothes.
Fair enough, fair enough.
What should I use? Is that okay? I will check. So do I use this? That's fine? Yeah, whatever works better. Okay. Hello, everyone. Oh. So we're gonna give a signal? Good. Wait.
Just wanted to just double check. In your presentation, do you have any videos with audio or anything like that?
I made sure.
Pretty much good to go.
Yeah.
Clicker if you like, how mic or handheld or podium, whichever you prefer.
All right, yeah. I'll use this. All right, thank you everyone for being here today. I think we're gonna get started here. So thank you all for being here today. Special thanks for those of you who took the stairs. My name is Ahmed El-Muqaddam, and I'm a senior scientist at Metrum Research Group. I'm so excited to be here today. I've been a Julia fan for a number of years now, and appreciate the opportunity to be here and talk to you about some of the work that we've been doing in Julia. So let's start with the title. So open source Bayesian hierarchical PBPK modeling in Julia. So let's start with a show of hands. Who here knows what PBPK is? Okay, so that's a good number. So for the people online, like 5 or 6 people, raise their hands. So if you don't know PBPK still, that's not the issue here. So PBPK, we're using this as a case study to represent the workflow. So this is the main focus of the talk, to demonstrate this workflow that we're able to put together using, with the help of Julia and Julia packages, that would allow us to do Bayesian analysis, specifically on PBPK modeling in our case, but it actually goes beyond that. So it can be applied to any ODE-based model.
So if this is the kind of model that you're interested in, then hopefully you'll find some value in this talk and some workflow that potentially you could apply to your own analysis. So what is PBPK? So PBPK, physiologically based pharmacokinetics. So let's start with the second half here. What is pharmacokinetics? I hope you guys enjoy my new cursor. It's a zooming cursor. I paid good money for this one. So pharmacokinetics, it's essentially what the body does to a drug or how the drug distributes in the body. You have a subject, you give the subject a drug gets absorbed till it gets to the systemic circulation, and then it distributes to the different organs, and then it gets metabolized primarily in the liver, and then it gets excreted from the body primarily through the kidneys, right? So this is collectively called ADME process. And that's basically what pharmacokinetics is about. Physiologically based because this approach is a mechanistic approach that incorporates tissue structures and blood flows. This will be clearer once we look at the model structure. But just a very brief history here. The concept of PBPK modeling has been there for quite some time, almost 100 years, first introduced by Thorsten Terrell, who is considered to be the father of pharmacokinetics by many, in 1937, where he drew this really nice diagram of a drug getting administered into the body, then gets distributed, absorbed and distributed through the circulation, governed by some partition coefficients, then goes to different organs, including eliminating organs, so the organs that will get rid of the drug, like the liver and the kidneys, right? Again, governed by some rate constants. So this was very cool, and it's been there for a while, but PBPK model hasn't really gained a lot of traction until the recent decades with the computational capabilities and the miracle solvers that are able to handle larger systems of ODEs. So this is typically what you would see in literature if you look at the PBPK model paper. So you would see that these compartments, they are organs, and the edges going in and out of the compartments, these are blood flow. These are flow rates into and out of this compartment. So for example, if you give a drug into the venous blood, it will go to the lung where the blood gets oxygenated, then goes to the arterial blood compartment where it distributes to different organs, and then passes through the organs back to the venous blood. If it's an eliminating organ like the liver or the kidney, it will get eliminated there, right? And the cycle goes on, okay? So we account here for a number of the major organs. If you have some unaccounted for body compartments, you just lump it into a remainder or rest of the body compartment. So that's basically it. And this is just a representation of an equation for one of these compartments. This is an eliminating compartment equation. And this type of equation here, this is the simplest PBPK model that you can have. This type is called the perfusion limited PBPK. I'm not going to go into further details into that. But just know that the ODE is pretty simple. So if you have the amount of the drug in this tissue, this is the rate equation for it. You have what's going into the tissue minus what's coming out of the tissue, right? Simple as that, which is governed by this Q blood flow rate into and out of the tissue. This is an eliminating organ, so you also have this additional term that has this clearance thing. This clearance is the ability of the organ to clear the drug. That's the rate of clearance from that organ, okay? So this is just to show you the type of parameters that we're interested in to build a PBPK model. So what are these parameters? So you have physiological parameters. These are like the blood flows or the volumes of these organs, right? These are physiological because they're independent of the drug that you're giving, right? And usually we know a lot about these parameters, right? From the accumulation of experiments throughout the years. So we know a lot about how the liver weighs, right? The other type of parameters are biochemical or drug-related parameters. These are like the unbound fraction of the drug, the clearance of the drug, the partition coefficients of the drug from the tissue plasma or the blood to plasma. These biochemical parameters, they are trickier to get. So how do we get these? Usually we do in vitro studies, right? Or in vivo in animal studies, or in silico, some algorithm that would compute, like, for example, the partition coefficients. These are very tricky to get, right? So some algorithms out there that would take some physicochemical properties of the drug, easy to measure in the lab, and will give you some prediction of these partition coefficients. So if you look at these two classes of parameters, I would say that almost always we are more certain about these physiological parameters than the biochemical parameters. All right? This will be important when we talk about the Bayesian inference. So introduction to Bayesian inference. Probably some people in the room would know more about this than I do, but I'll give it my best shot. So Bayesian inference is based on Bayes' rule. And this is Thomas Bayes, a mathematician and a minister, who proposed this rule. And it's a very simple rule coming from conditional probability. The task here is to infer this posterior distribution. Let's say theta is a parameter vector. Y is the data. We want to get the probability of the parameters given the data. So after you've seen the data. This is why it's called posterior probability, right? And we compute this through the product of the likelihood, which is the probability of the data given the parameters, and the prior probability of the parameters. This represents your prior belief, right? Your prior belief what these parameters should be. And you normalize or you divide by this probability of the data, okay? So it is a framework that allows you to inject your own prior belief, right, into the parameter or into the estimation or into the inference, which can be significant, right? Your prior knowledge can be significant. So usually we don't have, for most cases, this is intractable to calculate. So what people have been doing successfully is to use sampling methods like MCMC or Markov chain Monte Carlo samples. And there are very nice software tools that would do that for you, so you don't have to write this by hand. So MCSim, Bugs, Stan, a very popular tool, and Torsten, this is a library, a math library that we built at Metrum Research Group. Metrum Research Group scientists did this on top of Stan to be able to handle ODEs, to inject ODE solvers, and to handle the data, the kind of data that we deal with in our analysis. The last two tools here are Julia-based, and there's our general purpose tools, Turing and SOS, which are pretty awesome, and actually we use Turing for this presentation or for the work presented here. Why Bayesian PBPK? Well, it does make sense. PBPK models are built based on the wealth of prior knowledge of the system and the compound of interest, right? Bayesian inference, it updates the prior knowledge with the data, so it does make sense to combine the best of both worlds. Bayesian PBPK combines the best of both worlds, where you use your prior knowledge while at the same time using the data to update this knowledge and quantify the uncertainty. So this is just a basic workflow of how this would work. So at the middle here, we have the PBPK model working as the engine that would create the predictions. And then you inject the parameters that you're interested in inferring, the prior distributions of these parameters. Here you see the individual patient parameters. These are the physiological parameters that could vary between different individuals. Here you have the global compound parameters, which are the compound-related parameters. They won't differ between individuals, right? And these priors reflect our certainty or our prior knowledge about these parameters. So we have a pretty good idea where this physiological parameter will be. We have a pretty uninformed prior for this drug or biochemical parameter. And then it goes into the PBPK model. We get prediction. We go through the iterations of inference, and then we end up with the posterior probability. So why use Julia? Well, I don't need to tell this audience here, right, why Julia is awesome, but it doesn't hurt to reiterate. Solves the two language problems, so Julia is both efficient and expressive, right? It's open source, which helps greatly with traceability and reproducibility. But most of all, at least for me, this is the most important piece, composability of the ecosystem, that somehow it seems that the components of Julia ecosystem know how to talk to each other, right? So we use this here. So this was important for this work. And to demonstrate that, I'm going to go through the steps. So this is the take-home message here. So first, we define the differential equations using ordinary diffie-Q, so a SciML ecosystem. And diffie-Q callbacks is necessary here because we need to handle dosing events, right? So we need to handle this sort of events. And then what you come out of this is that you have an ODE function or an ODE problem that you can easily pass into SciML sensitivity or global sensitivity analysis to run sensitivity analysis, which can be important in this sense because if you have a lot of parameters, the model that I just showed had like 50 parameters, you don't want to waste computational power on parameters that don't influence your prediction, right? So you want to run the sensitivity analysis to figure out which parameters are more important to me so that I can do the inference. So especially if you're doing sampling, because sampling is slow, right? So this is seamless. Another seamless step, using Turing.gl, you can easily take that ODE problem object and just stick it in the statistical model function from Turing, and it just works, okay? Then you can take the output from Turing.gl and pass it, so the samples, you pass it into post-processing for MCMC chains for post-processing or stats plots to visualize the output and to look at the diagnostics. And finally, you can go full circle here, go back to ordinary DFQ, because our task here is to run simulations, right? We are confident about the model. Now what we want to do is to run simulations to explore different alternatives or different things that weren't in the data, right? So go back to ordinary DFQ to run simulations, use data frames meta, which I'm fond of, and chain.gl to work through the data wrangling processes required. And we use gadfly.gl for the visualization, which is an excellent tool. But we're also integrating into our frameworks algebra of graphics, which is also pretty awesome. So this is my plug here. So we're going to go through the case study. And this is a tutorial paper that we published recently, explaining this case study and going through this workflow, and also exploring another parallel workflow in R, Stan, and Torsten. Okay? So please check it out. I hear good things. So the case study, the model structure. This is the model structure. Okay? So I'm not going to go into details here, but the drug that we're looking into is mavoglurant. This was a drug that was a candidate for treatment of Fragile X syndrome, a genetic disorder that impacts brain development. The drug was discontinued because of disappointing results. So why are we using it for case study? Because data. Like, the data was available, right? Data speaks. So we took 20 subjects out of this data set. So this data set was PK data. So simply we inject the drug, and then we take blood samples from the subjects at different time points, and we measure the drug concentration at all these time points. And the doses that were given were 25 or 37.5 milligrams. So statistical models, so this is just to show you the hierarchical structure here. So hierarchical could mean different things to different people, but here I'm talking about random effects. So these are the effects that we don't have an explicit explanation for, or we cannot explicitly account for, right? So for example, if you look at C here, C is the concentration for individual I at time point J. So we assume some distribution around the typical value for this concentration with some measurement noise, right? Represented by the scale parameter sigma. So this is some noise that we cannot really explain, but we can estimate, right? The typical value coming from the PBPK model that takes the time points, the dose, and the parameters. We split the parameters into theta that we're going to estimate, nu that we are keeping fixed, and these are mostly the physiological parameters. These were the parameters that we decided to estimate, all right? Intrinsic clearance, very closely related to clearance. It's the intrinsic ability of the organ to clear the drug. The partition coefficients to the brain, muscle, adipose, bone, and rest of the body, okay? So notice here that this subscript I represents individuals, so this intrinsic clearance can differ between individuals, and hence the second level of random effects. This is the second level in the hierarchy, where we assume that this individual clearance is going to be distributed around some typical value with some omega scale parameter, which represents the inter-individual variability that we cannot really explain, okay? And these are just the prior distributions that we use in the model. Diagnostics. So this is good to look at the prior distribution of these parameters and the posterior distributions. How did the data impact your prior belief, right? So you can see that the data did impact the prior belief on these parameters, maybe except for this one, right? And the trace and density plots, these are just standard diagnostics tools that you would have with this sort of sampling technique. And these are just monitoring the samples across the different iterations, or the chains. These are called the chains. And ideally, you would have multiple chains to make sure that all of the chains are converging onto the same parameter distribution. And as my colleague at Metro, Bill Gillespie, would always say that we're looking here for fuzzy caterpillars. So if it's a fuzzy caterpillar, that's good. If it's a wiggly snake, that's not good, right? Because now you're not converging, right? And this conversion is also evident from the density plots, that they're more or less describing the same distribution, This is just the parameter summary. So now that we have the samples, we can compute whatever modes that we want on that posterior distribution. And these are numerical diagnostics that you get out of this. R hat, which is a measurement of convergence, the Gilman-Rubin statistic. And what you're looking for are values very close to 1. The SS bulk and the SS tail, these represents the effective sample size. I'm not going to talk more about this, but the larger this value is, the better, right? The less autocorrelation you have. So ultimately, we would like to compare with the observed data, right? So this is a PPC, which is posterior predictive checks. Now that we have the model, we can run simulations, which is pretty straightforward to do in Turing. You have the predict function, which is a convenience function that you can use to do that. So you overlay your predictions over the observed data. This observed data, these are the plasma concentration time profiles from all the subjects that we had, represented by the circles and the solid lines through the different statistics. And the blue ribbons here, these are the predictions. So you can see pretty good agreement between the observed and the predicted. So now we can run simulations, right? We can go wild here. So what if we dose 50 milligrams, right? So we can use this model with these parameters to run simulations on different scenarios. What if we dose every week, every other week? So this is the last thing I'm going to wrap up with here. So linear exponential. So this is a subtle thing, but I think it's important, especially if you have a larger system of ODEs. So if the DE model is linear, which means that you can present it this way, K being the parameter matrix, right? Then you can use this special solver linear exponential, which is more efficient than using numerical solver. This actually computes the exact solution that you have, right? So it is more efficient. We did this because our system was linear, so we can represent it in this way. And we did apply this, and the trace plots, they look good. And if we compare the output or the posterior predictive checks between the numeric solver and the linear exponential, 16 hours versus 4 hours, they look pretty similar. There are subtle differences, but they're pretty similar otherwise, right? So I think that this is important application. I just think it might need better documentation in the documentation of within SciML. So conclusions, Bayesian PK combines the best of both worlds since it uses the mechanistic prior knowledge available to build PBPK models and updates it with data while quantifying uncertainty through Bayesian inference. I'm going to be using as much as I'm using the zoom in. A framework was demonstrated that uses open source Julia tools to successfully run Bayesian PBPK analysis. The composability of Julia tools allowed for the seamless integration of different functions in the proposed framework, like sensitivity analysis, Bayesian inference, post-processing simulations. Linear complex models can be defined using linear exponential to be more efficient. The proposed framework can be generally applied to similar DE-based problems where prior knowledge might be significant. So, yeah, I would recommend if you guys are interested, go check out the GitHub repo, which is associated with this publication, the tutorial that I just shared, where all the code is there. I intentionally kept code out of the presentation to focus on the concepts, but all the code is there. So just a list of acknowledgements, and yeah, thank you, and be happy to accept any questions. Yes?
The distributed PBPK folks, they often emphasize or say that they use this. Do you disagree with that, or do you think it is needed here as well to have broader adoption?
Yeah, so I know this. This is a good point, and I think that things are shifting. Like, people are more accepting of running code because they're appreciating the flexibility, right? So you can have a nice GUI and everything, but if you really want to dig into the model, it will get you that far, right? If you really want to dig into the model and to add other components, like even for a single compartment, like if you want to add a tumor compartment, I've seen people just struggling with the GUI, right? While if you're writing your ODEs, you have a template, right? You have your own template. You don't need to manipulate it too much. And you just add an additional ODE for the additional compartment, right? So seeing that, I think that people's minds and way of thinking are shifting towards that. But yeah, I don't like GUIs.
What does the compute time scale with the number of parameters in this approach? If you double the number of parameters, what would happen?
Yeah, I haven't really done that. So I haven't done that sort of benchmarking. So I just went on with the 6 parameters that I had. I don't know how that would scale in this particular system. It's pretty efficient, and I did parallelization, which might be, make it more difficult to do the benchmarking, but did parallelization. One thing I would note, though, doing the parallelization, because you can parallelize the ODE itself, right? So using the ODE problem, so you can use ensemble problem. So this will parallelize across the individuals that you have, right? But you can also parallelize the chains themselves, like running the chains through Turing, right? So you can do both. But what I found is that it's not reproducible because you have nested parallelization there. So that was an issue for reproducibility. But yeah, it was pretty efficient. And actually, I was really surprised that the advantage that we get from linear exponential was only 4x, the ODE, which, says something about the very nice work that people at SciML are doing with the ODE solvers.
It also says something about the linear exponential, which actually is supposed to be about 2x faster, but we haven't.
Yeah, so the linear exponential is pretty good. I did compare it with Torsten. So Torsten also has a matrix exponential operator, and Torsten does it in 2 hours. Something to talk about. Yeah. So it's more efficient in Torsten, but it's much easier to write using Julia and SciML. Yeah, but yeah, it's really cool to have. Yeah.
So for these models, do you ever include patient characteristics in any way?
Yes.
Into the hierarchical representation?
Yeah. So actually, I did that here. So just for the time limitation, I couldn't go into all the details. But you have covariates of these patients, right? And these covariates would influence your physiological parameters. Could also influence your clearance term, for example, right? So I did have this covariate in the model. So yeah. You can also infer the parameters or the impact of these covariates. So you can assume some fixed value, or you can infer it as well. One thing I would also note, I have time. One thing I also note that one thing that I think is still lacking is to handle correlations. So in this example, we didn't have correlation between the random effects, but in other cases, you might have correlations between these random effects or variabilities. And handling correlations using Turing, so we found difficulty in using our go-to distribution, which is LKJ-Koleski. People use that all the time, and it works pretty well, but it doesn't work with Turing. So this is still something that needs to be worked on. Yeah, but other than that, it's pretty great. Any other questions? Maybe some zoom in. Yeah, you have a question? Okay. All right, well, thank you all. Thank you for being here.
Sure. We just move it.
Yeah, let me check.
So let me just replicate. No worries. Here.
Cool. Good start? Yeah. All right. Welcome, everybody. I'm Frederick. I work for Julia Hub. I'm also the idiot in the pictures there, if you have found me on Discourse or GitHub. And today I will talk to you about linear analysis and how we do that in ModelingToolkit. All right, so we'll start by talking about why we might want to do a linear analysis. We typically do a linear analysis when we have small deviations of our dynamical system from an operating point. So I had drawn a nonlinear function there and a linearized version of that function. And the operating point is the point in which we perform the linearization. So it's the point in which we operate our dynamical system. And this kind of small deviations from an operating point typically occurs when we have, for instance, vibrations. So if you think of a building vibrating, hopefully the vibrations are not too large. In electronics, we often do this with a small signal model. And in a control system, we might experience this because the controller is actually responsible for making sure that the deviation is small. So deviations are very often small by design. All right. And the workflow here, this is a messy slide, but we start on the far left with a nonlinear model. So this would be our ModelingToolkit model. We perform linearization using forward diff or symbolically. Then we obtain a large linear DAE model typically. We can perform some simplification on that if we would like, and then we arrive at a small linear ODE model. And then we perform more analysis on that linear model, and we arrive at some insight. So the very first step is to look at the interface to linearize. It's a function in ModelingToolkit. It takes the system. It takes a list of what you consider to be the inputs and what you consider to be the outputs. And it takes an operating point. So the operating point, OP, here is a dictionary that maps variables to values. And then it returns to you 4 matrices, A, B, C, and D. So those would be the 4 matrices in the linear state space representation you see in the bottom there. And this state space model now operates in delta coordinates, so in deviations from the operating point. And it also returns to you a simplified ModelingToolkit model. The next step is to perform the actual linearization. For that, we use forward diff. So we start with a system that is nonlinear. We have some dynamics function f that is a function of state variables x, algebraic variables z, some input variables u, and perhaps a time. And there are some algebraic equations and perhaps an output equation, y is equal to some function also. And after the linearization, we have this messy system on the right, but it's just a bunch of Jacobians of these 3 functions with respect to the arguments. The next step is to transform that to an ODE system. And I show you the code here just to highlight that it's actually just linear algebra to do that. It's very simple. If you don't have any algebraic variables, most of these things are actually of size 0, so then it's exceptionally simple. But even if you have algebraic variables, it's just linear algebra. Sometimes ModelingToolkit will fail to spot certain patterns in the simplification, and then you actually end up with a non-causal system, even though you expect a causal system. So a non-causal system in this context is a system that performs differentiation of the input. And we typically don't want that. So if we end up in this situation, we have a interface package, control systems MTK, that internally makes use of another package called descriptor systems that can perform another step of simplification for you to result in a causal system in the end. And the control systems MTK also contains a function called named SS for named state space. And that's kind of a convenience function that internally calls the linearization. And then it packages this into a structure that contains the linear state space system, and it keeps track of the names of the inputs and the outputs and even the state variables. So I will call this a convenience function in one of my examples a bit later. So we will have a look at a few examples of what we can do with this functionality. We will perform a modal analysis of a simple system, and then we will do some control system analysis. So mode analysis is not only an academic example, it's practically relevant. So here we see, on the far right, we see a building, and maybe there is some wind affecting that building, and it swings back and forth in the wind. And if we have too much swing back and forth, the people on the top floor will be nauseous. So we don't want that. So engineers will try to perform an analysis and figure out whether or not our design has an acceptable kind of vibration pattern. We can also do this for a bridge. So we have a bridge in the bottom right there. And if we think of a bridge as a kind of a flexible structure, that will also kind of flex in the wind and as trucks pass over it and so on. And it might be able to flex in many different patterns. And these patterns, we call them modes, and they have certain shapes. So maybe it will flex up and down, or maybe it will flex a bit like this and so on. And on the left, we have a drivetrain. So think of this as a drivetrain in a car or a truck, something like that. We have some generator or a motor that is acting on the, trying to drive the truck forward, and it's acting through some transmission. And that transmission is maybe slightly flexible. So you can look at this as two masses connected by a spring. And we might be interested in analyzing the mode shapes of this system. So here I have a ModelingToolkit standard library example. There is a QR code if you want to look at it. I've written a little function that just allows me to connect an arbitrary number of masses and springs. And once I have called this function, we see we have a, can I point here? Yep. We have inertias and springs and dampers. And I say inertia because it's a rotational example. And then I just connect n number of those. And in my example here, I will use 3. ModelingToolkit will give me something like this. It looks like a lot of equations, but that will mostly simplify down to a fairly small system. And once I have called this named SS function that performs the linearization inside, we see we end up with a system with 6 state variables. So 3 masses, they have 3 positions and 3 velocities. And this function takes the model as the first argument, then it takes a list of inputs, and in this case it's a single input, it's a torque I applied to the first mass, and my outputs are the velocities of the 3 masses in this example. And we see we have the 4 Jacobian matrices A, B, C, and D here. And this named state space system also keeps track of the names, so we have certain input and output and state names here. All right, once we have such a linear system, we can plot the frequency response. So here we plot something called a Bode plot. There are 3 curves in this plot for the 3 different masses. And we see that they resonate at different frequencies. So if I perturb this system at a particular frequency, we will get a very large amplitude in the output. But we also see that there are certain frequencies where one of the masses is standing completely still. So the blue mass here, the first mass, if I perturb it at exactly this frequency, that mass will actually not move at all. And we will look a bit deeper into that here. We can also say what happens if I hit this system with a hammer. So I compute an impulse response. And an impulse response is an infinitely large input force for an infinitely short time. And then the system will swing like this, the 3 different masses. We can try to ask about something called a damp report. So control engineers might be interested in this. Where we show the different poles, or if they are complex conjugated, we show the pole pairs. They have certain damping ratios and natural frequencies, and they might be associated with time constants. We can plot the mode shapes. So here we have 3 mode shapes. There is actually also a visualization here or an animation on the right. So this system tend to like to vibrate in one of these 2 modes. And the last mode is a rigid body mode. So it just means that all of them moves together without any vibration. So we can plot them we can plot the mode shape in the top there. We see the first one says that mass number 1 and mass number 3, when they go in one direction, the second mass goes in the other direction. And that's the animation we see on top there. And we can simulate that in time also. We see exactly the same pattern. So you can imagine that if this would be a bridge, you might divide the bridge into finite elements, maybe a very large number of those. But then you will have these kind of mode shapes that indicate that the bridge will sway like this, for instance. So this is a very common analysis you might want to do as an engineer. We can also have a look at the control systems example. Here we will make use of the ModelingToolkit standard library to assemble a model. And there is a talk on the standard library happening later today, so I encourage you to check that out if you're interested. we will assemble a model of a DC motor. So here is a kind of a picture of a bunch of different electrical motors. The final model we will assemble is a feedback loop here. So we have P for process or plant, so that's the thing we would like to control. And C is our controller. So C is the guy that typically makes sure that deviations are small from the operating point. In this case, the controller will just be a very simple PI controller. And the block here, P, it represents the motor. It has some electrical component, a resistor, inductor. It has an electromotorical force, and then it has some mechanical components. So this is kind of a multi-domain model that has both mechanics and electronics. I will not show the creation of all the components. You can refer to the ModelingToolkit standard library talk for that. But here we have a number of connections. So these connections form kind of the arrows you see here in the feedback diagram. It also forms some of the connections that happens inside of the P block. But an interesting point among these connections are that some of them have been given names. So some of these connections have a symbol as kind of the middle part in the connection. And the reason it's in the middle is to signify that this name belongs to the connection itself. So it belongs to kind of the lines rather than to any of the variables. And these analysis points are kind of small magical objects that behave in different ways depending on what you're asking the system about. So if you're just simulating the system, it's like they were not even there. They just disappear. But if you are asking for some interesting linear analysis, they might behave in different ways. So a control systems engineer might be interested in computing something like a sensitivity function. And I show them here. If you are not familiar with those concepts, it doesn't matter. The sensitivity function S is the transfer function from the reference to the control error. So typically we say, if I give a certain reference to my controller, we want the error to eventually become 0, right? We can't expect it to be 0 infinitely fast. That's unreasonable. But eventually we would like it to be 0. But most of all, we don't want this sensitivity function to ever have a large peak, because that typically is associated with poor robustness. And when I say robustness, I mean things like we use a model for this analysis and the design. And models are always terrible, at least if you ask a control systems engineer. Yeah, I will always tell you that no matter how much time you spend effort on your modeling, it's wrong. And we need to be robust with respect to how wrong it is. And the sensitivity function is a nice way of quantifying how robust we might be with respect to these errors. So the way this looks in code is that I ask ModelingToolkit for get me the sensitivity in the point y. All right? So that gives you the output sensitivity function. For systems with single input and single output, it doesn't matter if you look at the sensitivity function in the input or in the output. But if those are multiple input, multiple output systems, it actually does matter. So you can ask for the sensitivity function in the point u also, and that would be a different function in general. So here I plotted both the sensitivity and the complementary sensitivity functions. And if you are a control engineer, you might be satisfied with this. It looks the way we would expect. In particular, we don't have any uncomfortably large peaks in these functions. So then you might be happy and say that this control design looks okay to me. All right, we can also ask for things like a loop transfer function. So the loop transfer function is the transfer function you get when you go one lap around the loop with one connection broken. So if I ask for a loop transfer here in Y, what will happen underneath the hood is that ModelingToolkit will actually remove this connection here. So I have a red cross. So in that case, the analysis point acts as a kind of a loop break. And that is very often useful for analysis. So the alternative way of performing this analysis would be that you yourself modify your model so that the connection is not there. But that's kind of a hassle, and we don't really want to do that. We just want ModelingToolkit to handle it for us. So the analysis point is a convenient interface towards that. Once I've gotten the loop transfer function, I package that into an SS. I call the SS constructor from the control system package, and now I have a linear system. I can compute things like the H-infinity norm, so that would be the peak in the sensitivity function. Sorry, in this case, it's actually the peak in the loop transfer function. My apologies. I compute the H-infinity norm from the sensitivity function in the previous slide. And that peak is interesting because that's kind of a simple measure of robustness. And it also corresponds to this circle here in the Nyquist plot. So the peak is the peak of the sensitivity function is the inverse radius of this function. And if you're familiar with Nyquist theory, you might recognize that we want to stay far away from this called the critical point here. If this blue curve encircles this critical point, our feedback connection is unstable. So typically we would like to be far away from that point. And the reason we want to be far away is because this curve is associated with our model, and the model is wrong, so we don't actually know where the true curve is. And if we have actually linearized our system and nonlinear system, we know for sure that it's wrong because the actual system is not linear. So this gives you a very convenient interface between the nonlinear world of ModelingToolkit and the linear world that control systems engineers often perform their analysis in. Right, we can also perform simple analysis like compute gain and phase margins. So here I try to indicate with this green line, this point is where we would compute the phase margin, and the gain margin here is actually infinite because the curve does never intersect this real line. So this just to show that you can easily perform this simple analysis that you might be familiar with as a control engineer, even though you have a nonlinear ModelingToolkit model. All right, can you use this for more interesting systems, perhaps like a PD system? And the answer is yes, you can, and now the path is slightly more convoluted. We will not dive into great detail here, but we can model PD systems in ModelingToolkit. We might be interested in discretizing them, for instance, using method of lines. And after that step, we have typically a very large ordinary differential equation. We might want to linearize that, and then we have a linear version of that ODE. Typically, we might be interested in also doing some model order reduction if we do control systems analysis. We have a lot of those tools available to us in the robust and optimal control package. Things like balanced truncation and coprime factor reduction. So you can think of these methods as principal component analysis, but for dynamical systems. So they make use of the SVD and all that stuff. And no matter if we choose to perform a reduction or not, we might want to analyze this linear model. So we can do all the things we did for the previous control system example for PD systems as well. And if you are curious, there is a notebook on this QR code that tries to do this for kind of a very simple PD control example. All right. What are some other things we might be interested in doing? Very often we want to analyze our nonlinear system in multiple different operating points to make sure that we for instance, if we operate an aircraft, that is a nonlinear system, and the two most significant nonlinearities are related to the altitude and the forward velocity. So maybe we want to linearize this system in 10,000 different points in the forward velocity and amplitude space. And the linearization contains one step that is rather expensive. It's the structural simplification of the model that ModelingToolkit does. So we would like to do that preferably only once, and we can do that. So there are some utilities here in control systems MTK called trajectory state space and batch state space. And what they essentially do is they just perform the structural simplification once, and then you just linearize using forward if or something like that multiple times for multiple different operating points. And then you might be able to do, for instance, a gain scheduling design where you design multiple different linear controllers for the different operating points and you interpolate between them. And on the QR code here, there is an example that does exactly this. So there is a nonlinear system, linearize it in multiple different operating points, implement the linear controller and interpolate, and there is a ModelingToolkit component that represents this gain scheduled linear system that you can make use of. And there are also some utilities to help you treat a collection of linear systems as one uncertain linear system. So if you plot that, you get kind of a distribution of Bode plots that might be interesting to analyze. All right, we have a number of additional resources. There is, of course, documentation on the linearization in ModelingToolkit. Some of the linear analysis documentation belongs in ModelingToolkit standard library, and there is a particular reason for that. So the analysis points are inherently a causal concept. You have to have a notion of an input and an output for those to make sense. And ModelingToolkit is an a-causal program, modeling language. So ModelingToolkit doesn't actually care about inputs and outputs. But there is this particular sub-library in ModelingToolkit standard library that implements blocks that actually are causal. So a PI controller is causal. It has an input and it has an output. So that's why it belongs there. There is a link to JuliaSim control. So it's our Julia Hub library for control that adds more sophisticated functionality on top of the open source control systems packages. We have a lot of linear analysis examples there as well. And then finally, there is a YouTube video where I go into a bit more detail about why we need the analysis points and why it's awkward to try to do this analysis without them. There is also some future work, and maybe you have seen the little demo at day one here about the graphical user interface we are working with. All of this fits very natural into a graphical user interface workflow. So you have your components, your block diagram there, you have your signals to name them and to ask for, give me the analysis, give me the sensitivity function in this particular signal, and to integrate all of that into a smooth workflow in the graphical user interface. All right, and that was my final slide. So with that, I would like to thank you for your presence.
Only one thing is feature work, everything else is done.
Yeah, for linear analysis, there is only so much you can do. When you linearize the system, you got it. And then what you do with that linear system, you can do a lot of interesting things with that. But yep. Yep.
If you have a model that you can't handle, generally decoding it symbolically.
Sure.
What does it do?
Sure. If forward diff doesn't handle it, it will just throw an error in your face. And what we then suggest you do is you can do data-driven methods like frequency response analysis. So we do have such methods implementing in the JuliaSim control package. So that would be, if we consider forward diff the infinitesimal kind of linearization, this would be a finite kind of linearization instead. Yep. You could easily do that also. You could swap out forward diff for finite diff if you would like to do that. Yeah. Yep.
And there is a new type of decoding too as well, because the JuliaSim compiler pieces.
Yep. So the actual linearization, we used forward diff there because it's simple. You can switch it out for the symbolic linearization because sometimes for small models that gives you some insight if you have linearized the nonlinear system symbolically. But there is nothing preventing you from doing any other linearization. Yeah.
If you have a model that has sort of a block diagonal structure where some blocks can linearize symbolically, other blocks can't linearize, kind of stuck and you have to linearize the whole thing there.
In this case, yeah, we would be stuck there. We don't have anything special case to handle that. Yep. Yep.
For the analysis points, does that have to be specified with the modeling model, or can you use more like generic state-based object or something to specify the analysis points and then do that
So all of the downstream analysis, it doesn't rely on ModelingToolkit at all, actually. So you can, if you have a linear system already, you can already use this, the analysis tools. The analysis points only make sense in the context where you have these connections between ModelingToolkit points. If you don't have those connections, you are kind of on your own with respect to calling the lower level linearize function, where you just provide, here's my input and here's my output. But if you look at the video I showed there about the video on how to linearize the ModelingToolkit model, it's awkward to do that, especially if you have a model that simulates. That model does not linearize. And I go into the details why that is the case in that video. And it has to do with the structural simplification will consider your linearize, when you try to linearize, we'll consider that you have too many variables. Because now you add an additional input, but the model is already fully specified. So you kind of need to you need to unspecify the input before you actually perform the linearization. And that's the awkward part. It's awkward to work with. So the analysis point make that a bit easier. But you can do it manually if you want to. Yep. Yep.
Can you talk about what you do for the discrete side? Because at some point you're going to want a state space system of your controller as well.
Sure. We do this. We had a yeah, we don't handle it, is the unfortunate answer. Yes. Yeah. Well, yeah, we handle the simulation of it, but it's not handled at all in the linearization, so we would have to add that, yeah. But obviously, we should do that, and we will, but it's not there at the moment. Yep. Yeah. Yeah, sorry to give you an unfortunate answer there, but that's the case. It will happen in the future. Yep.
Future works better than not going to be worked on. So.
Yeah, yep.
Yeah, and it'd be interesting to have partners for which they want to actually use the things that are mixed in discrete and continuous. So if you have models or if you want to come work with us, come talk with us.
All right, cool. Thanks.
Folks, just to let everyone know that the group photo for JuliaCon is taking place outside at 12:30, about 5 minutes. If you all want to go out to the green, that'd be great. If you want to take part.
Hey, nice to meet you, finally.
Good to meet you in person.
Yeah, we'll meet down there.
Yeah, sure.
I know. No, it's one
Yeah.
you have a USB-C? I think this might work. It is this it? Yep. Connect and see, I don't know. Yeah, that should work.
Are any of the speakers here for the session? Okay. Do you want to introduce yourself instead of me introducing you? Yeah. Okay.
Do you want to try?
Yeah, please. Should be.
Thank you. There we go. Okay. Thank you.
You want to try?
So we're going to be starting soon, so at 2. Last call, if you're a speaker, and I don't know your name, and that's what they're doing. Yeah, I won't do last call for speakers. It's like your speaker and we have to check in. Oh, yeah, I got you. Okay, you're Nina. Okay, I got you. Anyone else?
Can I start? So good afternoon, everyone. I'm Sharan. I work for the JuliaSim team at Julia Hub, where today I'm going to be talking about surrogatizing dynamic systems using JuliaSim. There's a new product which is called Digital Echo, which is in fact demoed by Chris in his
sponsor talk, but I'll be talking about it in more detail today. So let me just briefly discuss the agenda for today. Yeah, so I'll start off by motivating the problem. Why do we need to surrogatize? Then what a surrogate is. Then we'll talk about reviewing the current prevalent surrogate generation pipeline. What do people do today? And then I'll go about introducing digital echo, which is our solution to this problem. And then I'll go on to explain some examples using digital echo. So to start off with, imagine you're a chemical plant engineer, and this is the chemical plant you're in charge of. And you need to tune the parameters of this chemical plant on a regular basis depending on the prevalent conditions, right, and the required output from the plant. And for the plant like above with a sufficient number of complexities and sufficient number of subsystems which have their own independent physics going on, it's very computationally intensive to simulate such a system. Even if you have the physics of the system kind of written down in code, to simulate such a physical system takes forever. It could be in the order of hours or days even. And this is prohibitively expensive, and it negatively impacts the productivity of the plant. So this is what we are trying to change, right? We are trying to make such a chemical plant engineer much more productive on their day-to-day basis. So here, what we see is the power of speed. So the first block you see is kind of a representation of a single simulation being run by a single chemical plant engineer. The second one is, say, a group of such simulations. It can be either run by a same person for multiple different parameters, or it could be like different, like a group of people running different experiments to decide parameters on. And as you can see, as we kind of scale it up, we are able to So once we scale it up to a larger scale simulation where we are able to do hundreds of such simulations at once or in a short span of time, we are able to kind of liberate that chemical plant engineer into doing all this experimentation on his own, or do it in a much shorter period of time. Instead of in a matter of days or hours, it could be in a matter of like seconds even, right? We have had real world problems which we have solved, which take much, an order of magnitude, several order of magnitudes less time after the speed up using a surrogate. So yeah, the main reason we want surrogates is faster workflows. And faster workflows are enabled by faster such components. So each of those individual components have their own complexities. But if we take the slowest component and speed it up, that itself saves a lot of time. And what this enables is faster parameter optimization or faster control design, which is very crucial in any research or a production setting. So I keep talking about surrogates. So if someone isn't aware of what surrogates are, they're essentially machine learning models of physical systems. They are fast but approximate models for a given physical system. So when I say approximate, they approximate pretty well, and they're very, very fast, right? And I'll demonstrate some examples soon. So let me first discuss the current pipeline, which is often followed by the industry, and the problems with it. So whenever I say a machine learning model, obviously you need a lot of data. So that means generating the data set first from the physical system. This essentially involves training it with different parameters, different control settings, and is a very hard problem to solve because how do you know what kind of control systems are required, right? And it's a very expensive, computationally and like technically, it's a very hard task. And once you have the data set, the next thing you want to do is pre-process it, because that's something which is often non-trivial, because based on the model you're dealing with, you will have to pre-process it in a certain way. And that is always an expert thing to do. You need a machine learning expert to do all of that. Often, each of these individual steps which you see above are often handled by different teams, and they have to kind of work in sequence, and it's very hard to parallelize these jobs. And that kind of slows down the entire process of surrogatizing a lot. And that would basically bring down the productivity of the entire company by a lot, because each team is waiting for the previous team to get their work done, and it's a never-ending thing. And even after you have a prepared data set, you have to choose and configure the model and tune it, which is not at all trivial. You again need a machine learning PhD for it. And then you want to train it. Training involves HPC. It involves kind of parallelizing it. It involves GPUs, which is all, again, a big headache, right? Then we want to validate it and deploy it. Deploying, again, involves a lot more technicalities, which often companies do not want to deal with. So what our pipeline, the Digital Echo pipeline, enables is it gets rid of the three most painful processes, which is pre-processing the data set, configuring the model, and even training the model. All of that is automated for you. So we have our pre-processing pipeline, as well as, which is followed by the training pipeline, where we configure the model for you, and the training also happens in an automated way on the cloud by using all the resources available, right? As many GPUs as needed, as many CPUs as needed, right? And that is what makes this process faster, and even for a surrogate engineer. So yeah, so to enable all of this, we introduced Digital Echo. It's essentially an automated framework for generating accelerated, high-fidelity digital models that can reproduce the behavior of your simulator process. So when you use the Digital Echo product, the first thing you will want to do is kind of specify what kind of data you want to generate, right? And that essentially involves telling what kind of parameter space you want to work in, or what kind of control space you want to work in. And that's all you need to do, after which the rest of the steps are kind of handled by the pipeline. And you only need, like a domain expert only needs to care about what they are aware of. They are aware of the parameter spaces. They are aware of what kind of controls they deal with. Everything else is, they don't need to worry about it at all, right? That's the whole point. No machine learning expertise is required to get this done. And it scales in various kinds of surrogates, both full model and component model surrogates with a single API, right? Let me show you a demo, which was, I think, already discussed in the sponsor talk, but I'll explain it in slightly more detail. So what we are trying to do here is we are trying to surrogatize a pack of batteries, pack of electrical cells, which makes a battery. And as you can see here, these batteries are often used in electrical vehicles nowadays, and it's very important that you get accurate predictions of the charge cycles so that your car doesn't stop halfway, right? And as you can see here, the left-hand side is essentially without a surrogate. If you try to simulate this whole process, it takes very long time. It's like the car is not even moving. But when you look at the right-hand side, it's with the surrogate. It's just trying to demonstrate the speed of the surrogate. And in this case, it's the speed makes it like order of magnitude difference in how you want to deal with that physical system. So coming to the properties of Digital Echo, right? Often when we say a machine learning model, we say like it turns out to be some sort of a neural net, which is fully black boxed, and there's no sometimes there's no theoretical grounding to any of this. So that's the first thing we were thinking about. How do we make sure that people can trust this system, right?
The idea behind digital echo is that it relies on well-studied theory of topological conjugacy, which essentially means that there exists this alternative topological space where the dynamics are easier to kind of simulate, but at the same time, you won't lose out on much of the information, right? So we essentially map our existing space into this topologically conjugate space where it's super easy to simulate, super fast to simulate. The system is not that stiff anymore, and that makes all the difference. This is what has enabled us to get the state-of-the-art method in SciML in terms of both accuracy and performance, that is speed. Right? And the second most important thing here is probably we are tightly integrated with all sorts of standard modeling tools. So to start off with, the first thing we want to support is obviously ModelingToolkit within Julia. And this allows us to make use of the wide array of SciML solvers, like these high-performance solvers, which are proved to be great. I think if you have attended Chris's talk earlier today, we know that these solvers are better than the defaults found in most other systems. And we make use of it, right, when we are in the SciML world. And a lot of it is built on top of ModelingToolkit, and it has first-class support for ModelingToolkit. At the same time, we know that not all the people who want to use this might be familiar with ModelingToolkit or Julia. So what we also enable is to import these physical models from outside by supporting the FMI, that is functional mockup interface. And this enables us to kind of import models from any other external simulation device which supports FMI, which is most of the good ones kind of support that. So good ones support that. So you can be sure that you will be able to use this product irrespective of which kind of ecosystem you come from. And another thing is that we can integrate these fast surrogates back into the simulation environment, right? As a drop-in replacement for your current systems. So you have a current system which you know works well. It's a physical system, but you know it's very slow. So what you can do is you can create an FMU out of it and just put it into our product, and it will give out another FMU, a faster FMU, an approximate FMU, but a very fast FMU, right? And this can be a drop-in replacement for that existing subcomponent. And what this enables is that you don't have to change all of your pipeline at once. You can go about experimenting with just one component, which is the most painful one. And that way, you can slowly kind of convert your workflow into a faster one, right, in a step-by-step manner. The third thing is it's fast. It's extremely fast. It's faster than anything which is out there right now. And it's because of this theory of topological conjugacy, and we are able to find a right mapping. That's the main thing here. We are able to find a right mapping onto this easier to simulate space. And this is what makes our surrogates blazingly fast when compared to the original simulation. So let me discuss another example, which is the brusellator. You might have heard of brusellator if you come from the SciML world. It consists of essentially two partial differential equations, which represent two different species, and it's considered a very stiff, very complex model, and it's often used as a benchmark for various solvers. And it used to be unimaginable to think about surrogatizing this because of the stiffness of the system. But we have been successfully able to surrogatize even such systems, even such theoretically complex systems, and produce order of magnitude of performance gain. So here we are able to speed things up, but that's not everything, right? What do we do with the speed? So we need to think about applications using the speed, right? And one of the major applications which I discussed earlier is parameter estimation. And we are able to do that with digital echo on brusellator
very fast. If you see the right-hand side, you can see the speed at which it's able to fit to the parameter estimation is able to fit and like converge. And this is all enabled because of digital echo, right? As I said, you can use the digital echo as a drop-in replacement for original model. That means that you can use it as a drop-in replacement for parameter estimation, control tuning, all of that, right? Yeah, this is something which I discussed already. So essentially, because of all the speed up, you're able to kind of democratize a lot of these simulations. You don't need to have in-house crazy amount of compute to run things in parallel and still take days to simulate them. You can do all of that on the cloud while using the best of infrastructure, and you can train using the best of infrastructure too. So let me delve into slightly more detail into what a workflow looks like for an actual developer now. And so as you can see here, the first part is essentially, most of the work is essentially data generation setup, right? That's the only thing the user really needs to worry about. That, okay, what is my parameter space which I'm interested in? What kind of controls am I interested in, right? And what kind of time span am I interested in surrogatizing over? If you have this information sorted out, then you're good. Then we take care of running parallel jobs, thousands of parallel jobs, and generating thousands of data samples which are required for the surrogate, right? And all of this is done by using the Julia Hub platform, where we are able to run these massively parallel jobs on Julia Hub in a much more scalable way. And once the data generation is complete, we have all sort of visualization tools to help you kind of see how the data looks like. Is it covering the spaces you really wanted to cover, right? You can have phase space plots, you can have trace plots, and we have an entire visualization suite dedicated for that, right? Apart from that, in this example, we also show how you can kind of validate this in both open loop and closed loop setting. Open loop is hard, but it's not that hard. But closed loop is often known to be very hard to actually allow. What I mean by closed loop is essentially we test this surrogate on a controller which takes back the observables as the input, right? The controller decides the next set of inputs using the previous observables. And all of this means that we are actually learning the underlying dynamics. We are not trying to curve fit like most machine learning models do. We are actually learning the underlying physics or simplified versions of the physics. A reduced order model, it's a reduced order model where we are trying to learn the physics underneath. And that is what is enabling us to achieve all of this accuracy and while retaining the performance, right? Or while improving the performance even. So one other thing to note here is that some of these plots, I think the third plot here is this. Yeah, the third plot here, you might notice that it is more of a qualitative fit for a transient region. So what the kind of approach we are taking towards this problem is that often engineers are very concerned about the steady state of the system, that they want to make sure that they get the right steady state. But the transient behavior before attaining the steady state is not that much, it's not quantitatively important, it's qualitatively important. So even if in some crazy transients where we can't fit the quantitative behavior, we make sure we fit the qualitative behavior, right? So that way, like a real world application of this would be that if you have a control you're trying to tune, if it's unstable, you'll be able to detect it, right? That's the whole point of it. So the first example was using an ODE problem source. So as I said, we allow importing models from various sources.
including ODE problems from MTK. And the second example you see here is from an FMU source, right? And the API remains almost the same, right? There's the only, instead of plugging in an ODE problem, you'll be plugging in a path to an FMU, right? So that way, your workflow is unaltered irrespective of the source. And you can see here that it's again the same thing where you specify the data gen and the training is taken care of. Also note that you might, it might seem that these are toy models, couple clutches, but these are only to demonstrate so that you can quickly run this on our platform because they are super easy to simulate. We have tested it out with all sorts of more complex systems like batteries and HVAC. So apart from having a MTK source or a FMU source, sometimes you already have real-world data. So we have had clients come to us who say that, okay, we already have a data set collected from real-world trials, and how do we model this, right? So we also allow for that. So as long as you have data set in a certain format, which is specified clearly in our docs, you're good to go. You can model that physical system. Even if the physical system is completely unknown to you, it doesn't matter. You can still model it comfortably. So do check out our docs. This is all live as of a couple of days ago, so you can, it's actually part of the free tier of Julia Hub, so you can go out and play around with all of this. And do let us know what you feel and if you like it. And if you are interested in any specific aspects of this, please reach out to us at the booth. We will be open to any questions. And any questions now, too.
So how does this integrate with model analysis tools, such as like sensitivity analysis? So can you still find out about physical parameters despite making a surrogate of the actual model?
Sure, that's something which I was talking about with the parameter estimation. So yes, any sort of model analysis tools, it's a drop-in replacement for the original system. So you can do any sort of analysis with this too. And so say parameter estimation, you can do that. Also, we have in-house such analytics tools. We have Model Optimizer, which I think is separately being presented. And we also have JuliaSim controls optimizer, which is, again, a control tuning framework. And all of that supports digital echo. But also another way to look at it is that even if you get it from an external modeling tool, then you can still convert it to an FMU and go back to your analytics tool of choice. You don't have to stick to our thing. If you're more comfortable with something else for now, go ahead, use it, right?
I think that the key thing is that a feature that's coming is not 100% done yet, it's like 1 month away or something, is that these will be outputting the models as ModelingToolkit models themselves. So essentially you have slow ModelingToolkit model come in, surrogatize, fast ModelingToolkit model come out, right? And that then kind of completes the loop to make it very easy to integrate everywhere. Not 100% done, there is a hiccup there, but it is the next thing to do.
And yeah. Okay. There is a limitation. So one main limitation is that, as I said, sometimes when your signal is super noisy, you only get to fit it qualitatively, right? And the steady state is, however, achieved. Like you can attain the steady state. And yeah, apart from that, so yeah.
I think that there is one major limitation to mention, right? And the limitation is that this, as a surrogate methodology, is a convergent methodology, right? It's designed in such a way that, if you think about the surrogate problem, you have a simulator that's effectively generating you data whenever you want. And so if you set this problem correctly, you should be able to have an infinite data source and training machine learning to do as good as you want, right? But that means that what we cannot necessarily tell you up front is how long it will take to train the surrogate, because it might say, oh,
Yeah, so the amount of data you need varies from problem to problem. And the kind of diversity of the data generation is something which only comes with a large amount of data unless you specify it perfectly, right? Yeah. Mm-hmm.
Well, two-phase flows have a phase change that happens in the dynamic that is 10 to the 10th order, so 10 orders of magnitude larger than the standard dynamics of other components, and we show that at the case.
Yeah, another thing which is good to mention here is essentially there is an aspect of how fast your dynamics are, and you can tune your model for that. So if you know beforehand that your dynamics are super fast, you can make the model look at it in such a way that there is a time constant involved where you can tune it to capture even a super fast dynamics. Yeah.
There's also a battery example where the current is oscillating really quickly.
Yeah, so the battery example is, yeah. So if you look at it here, you can see how fast the dynamics are, and it's still able to capture it.
No, that's the current, that's the output.
Yeah, this is the current. So you can see the dynamics are pretty fast, and it's still able to capture it. And sometimes, even when the transient nature of the thing is also captured, right? Any other questions? Yeah.
Is this able to handle like dynamical models where, like, depending on the parameter regime, like it's very different behavior? I guess like the classic examples like low Reynolds number flow versus high Reynolds number flow.
Mm-hmm. Yeah, that should not be a problem. Yeah.
But the data gen would have to explore both regions.
Yeah. So the data gen is responsible to kind of, explore all sorts of dynamics. That's why those phase plots which you see, which you saw earlier, are basically, the purpose is to aid that, to make sure that you know that all the phase space which you are interested in is actually covered, so that we can capture the dynamics there.
When we create surrogate models, like compound models, we find that the quality of model and the speed of training varies enormously with the choice of the architecture.
Mm-hmm.
Is that something that you've kind of considered in your work, or you've just chosen one you think is good for you?
Yes, we have experimented with a ton of different architectures, and what we were aiming for is not just training speed, it's about whether it's able to generalize, whether it's actually able to capture the dynamics with a minimum number of parameters. You don't want to just give it a lot of parameters, it will just overfit, right? And we also are trying to avoid stuff like recurrence, which are often super expensive to train. Those sort of things are being avoided at all costs. Yeah.
I mean, and there's also some other tricks going on with things like, like reservoir computing techniques, right? It can help make the optimization process not as optimization, right? So there's other tricks going on involved. But I think the key thing, though, is to meet the data gen, right? Pretty much any architecture can do well if you give it the right data. And, and by taking, the main difference that we've done this year with the surrogates is taking control of the data gen process and saying, we want to make it that way. We force the exploration of rate space to build a data set that we know will work. And that's really the key difference.
I guess that's it. Thank you.
So you moving to the next picture?
Yeah.
Ah, good.
This trails.
So you guys can introduce yourselves and all that. So.
Okay. You set up the laptop.
Hey everyone, we are the next speaker. There's three of us. I'm Torkel.
I'm Vaibhav.
I'm Utkarsh.
And we're going to talk about, well, do you want to start the introduction?
Yes.
Should we do add a clicker?
Why? No, I think it's fine. Okay. Hi everyone, I'm Vaibhav Dikshit. I'm a software engineer at Julia Hub, and I'm going to be joining the Julia lab here at MIT starting next month. So what we wanted to do today was just sort of, I mean, last time we had a JuliaCon physically was 4 years ago, as we have been talking about since the day one. And since then, SciML, both as a software ecosystem and as a field, has sort of just taken this huge explosion, right? I think at this point we have around, I don't know, at least more than 50 packages, right? And a lot of things that you want to do with tools, it's often, even based on the feedback we were getting in the Birds of Feather on systems biology earlier today, it seems like there's some disconnect in terms of what's available already in the ecosystem and just in terms of users not being aware of it. So just to give a sort of sense how much of an impact SciML is having, right? All like these are, you can see like very distinct fields like geoscience. There's like, I don't know, there's physics and epidemiology and stuff like that, right? And all of them are using the same software stack and same like very similar techniques. So I think that's like a very unique, a very unique situation we are in. And I don't think there was this sort of sharing of tools and techniques across these different fields before. Cool, and we have been talking about this, like even in the keynote, Chris sort of covered it. What actually enables that to happen, right? Is it just that, differential equations.jl is like the fastest solver of differential equations out there, and then we just put neural networks in there, and that's why SciML is SciML? Well, kind of, but then there's other things also, right? I mean, you need sort of this support of various, what used to be very separate verticals in scientific computing. You want to be able to sort of support very different architectures, right? Someone will just want to run experiments on this laptop. Someone will want to use GPUs or even, I don't know, TPUs or something. So you want that. You want very fast solvers, not just for differential equations, because differential equation solvers don't exist by themselves, right? You need linear solvers. You need nonlinear solvers. So you need a robust ecosystem where you can swap in all these parts that make up the entire solver domain, right? And then for users, what really matters is how you write out the models, right? We used to have this functional interface, but now we are moving towards a symbolic interface with ModelingToolkit. So modeling domains requires some domain-specific languages, and we have, I think, gone a long way just with ModelingToolkit for it, but also some other very much more narrow focused DSLs, which you'll be able to see later. And then also, obviously, the ML in SciML, right? You need machine learning libraries, you need optimizers. And then because you're not dealing with you're not just fusing together linear functions, it's not just neural networks, it's actually much more complicated likelihoods when you're dealing with these SciML architectures. You don't want to just rely on the traditional machine learning optimizer. You need a way to be able to experiment with different things. You might even want some uncertainty quantification, so you need ways to solve Bayesian inverse problems and everything. And then you need to be able to analyze results. Like that's sort of obvious, I guess. So all of these things have to work together with an interface that sort of works together, right? It can't be that a user has to go and learn each of those separately, and then, yeah, that's too much of a learning curve. So why is Julia and why is SciML? Well, if you missed that, it was like, why is Julia SciML specifically suited for it? That's because we have all of those. And
as I said, right, we have grown to this large organization. We have a lot of packages, and this is not comprehensive at all. Literally, I think I know at least 4 or 5 packages on the top of my head, which are not here, but that was sort of a limitation of the space and just in terms of the expertise we 3 shared and couldn't cover everything. So I'll hand it off to Torkel, who will be covering some of the modeling tools available, and then maybe, and we'll also be interleaving our sort of, we'll be walking over the ecosystem basically, and we'll be interleaving that with some demos and some code examples that you can see.
Does this work? Okay. So I'm just going to want to talk through like a couple of the things which the modeling package is built upon. The first one, symbolics.jl. This is an interesting one because it really, to me, does 2 entirely different types of things. So the first thing, it's a computer algebraic system. So it allows you to represent, say, an equation symbolically. And then, for example, if you then write your equation, you want to take the derivative, it does this entirely symbolically. So it's a very powerful engine in this sense. Second, what this do, it can act as a base for a lot of the tools that builds modeling within the SciML ecosystem. So it means a lot of the models that you build deep down internally is entirely symbolically represented. And this allows a lot of the tools to do some kind of fancy stuff. For me as a modeler, like I only encounter symbolics in the second sense, which means that practically I never encounter symbolics at all, because it's something that happens deep down. But we think that this can be quite good. Like if you hear about symbolics, this is basically what it does. And next one, ModelingToolkit, again does a little bit 2 types of things. The first thing, which again for me is kind of important one, it creates an intermediate representation for representing SciML models. This is typically a differential equation model. And the idea here is that you have 2 types of people doing modeling here, working within the system. You have people like build modeling packages, which creates a model. Then you have people that build tools which does things to this model, say do simulations, sensitivity analysis. And really the promise here in ModelingToolkit is that it implements one intermediate representation. If a modeler can create or represent their model using the ModelingToolkit way, then they have all of these analysis tools automatically working on the model. In the reverse, if I want to make a new tool, as long as for, say, model analysis, as long as I make my tool work on ModelingToolkit type representation, it will have access to all of these kind of modeling packages when they're from electronics or biology or something like that. And I think this is quite a powerful thing within the SciML ecosystem, that we have this representation which allow people from many different domains to collaborate. And then the second thing that ModelingToolkit does also, it actually allows you to build these kind of models by writing the equation directly. And I'm going to briefly show this in an example. And actually then have various packages which feeds into ModelingToolkit to allow you to build models. One of them is ModelingToolkit standard library, which just implements a lot of like ready-made modeling components which you can connect. So it can be like a capacitor or resistance in an electronic circuit, and you can just connect them to create your model. So that's one thing you have. Another thing you have is domain-specific modeling languages. So say, for example, I work in biology, I make a typical specific type of biological model, so then there's a packet catalyst for creating these models. There's the orbital trajectories, if you have like, I think, satellites that goes around, and then like there's a specific way to represent these models, and you have these separate packages. But a lot of what this one does is actually like feed in and create a ModelingToolkit model, which then connects it to the entire SciML ecosystem. So if so now I'm just like briefly going to show how like these kind of models appear in real code. I think we're going to start with this one. Wait. Some slight technical issues, soon sorted out. Okay, very nice. So I want to start with this one. Don't you have the NPC set one? Okay, so there, this is an NPZ model, which is like a very common thing when you model plankton in the ocean. Basically, you model the amount of nutrients, the amount of photoplanktons, Very good. The amount of photoplanktons, and see how these interact. And this creates a very normal, like a differential equation type systems. And here we use ModelingToolkit to, so basically, okay, we want to create a model. First, we declare what parameters we have. Here I've simply called my parameters A, B, and C. And then what kind of variables we have in the system. Of course, we have T, it's going to differential equation, depends on time. And then we have some time-dependent variables, and the amount of nutrient, P, the amount of photoplanktons, and Z, zooplanktons. And then we define the differential, a differential. And then what ModelingToolkit allows you to do is basically write equation in pure code. So here we have differential equation for amount of photoplankton, which plankton, I think, like gets sunlight and grows. So you see here, for example, there's a growth rate, which is the amount of nutrients and the photoplankton, so normal growth things, times a parameter. And then you have a death rate, D, which is basically to get eaten by the zooplanktons. And here we have like normal death. So this you can do in ModelingToolkit. You can do a very similar thing to create a partial differential equation. So here we have x and y, basically like a space. We create a variable u, second derivative with x and y, and then we create an equation, which is the xx, so the two derivatives with respect to x and y. If you add them, you get 0. And then you set your boundary conditions, your domain, so like where the model is, and then in the end you can kind of combine everything to a partial differential equation system. And then finally, we're showing off so this here you write the equation directly, like one alternative is your domain-specific package, and here you do something, in this case is called Catalyst, and here you create your model slightly different. Here's called a sigma general system. And I'm just going to briefly, like biology must understand what's happened. Here are basically reactions. So we have empty set to sigma, like creation, degradation of sigma, creation, degradation of A1, A2, A3. So this is a variable of the system. And then we write some rates here. But this is basically to show you that if I do a specific type of model, I know more about my system than just the differential equations. And I can actually use this when I create my model.
So I'll be talking about some of the work that we have, like with the solvers. Like let's say now we have model our system. The natural question is like how we solve them. So basically, the very go-to software for this is like differential-equation.gl, which is like built on a lot of small packages. So let's say if you don't know, let's say if you are working with an ODE, you don't know what solver to use, or like you really are like not very aware about your model. It has like a lot of features like such like automatic solver choices, selecting proper linear solve methods, which are like built into that, and that's why it's a very quite a heavy repository. But let's say if you want a more fine-grained control, let's say you know now about ODEs, and you know, let's say it's a stiff ODE, or let's say it's a non-stiff ODE, you can use like ordinary diffq to solve basically like ordinary differential equations and differential algebraic equations, which are like have like a lot of constraints of the algebra in the mass matrix form. And moving on that, so similarly, let's say if you now know there's some stochasticity involved in your model, then we have some different packages to like basically use to simulate stochastic differential equations. And I think the lastly is like now, okay, now let's say if you know something about the discrete processes, like I think jump processes also covered yesterday, and I think you should visit that talk, which basically do a lot of simulations by Gillespie algorithms of the jump processes. Finally, like some of the things that we have, some of the advanced solvers which are like not really commonly available, also about the delay differential equations, which basically extensively covers like where there's like a lag in your ordinary differential equation model. And bringing this all together, this is like moving across the abstraction that we started from ordinary diffq. We have a very high fidelity solvers, like building all the stochasticity and the delay differential equation model together. So we have another package called stochastic delay differential equation models. And finally, so we support a lot of, quite a lot of solvers in that, and we also strive to use the solvers which have existed before. So Sundial is one of the packages, which basically is like a wrapper over the C++ differential equation solver library. So CVOD, BDF, like these very common solvers which have like people use. So we provide that interoperability instead of like not, let's say you're suited for some of the optimization tricks which are like done in those solvers. So these are like some of the things that Sundials provide. And similarly, like on the line of, let's say, this is like a more of a high level, on the partial differential equations, like method of lines. So the way to basically like simulate PDs is by generating semi-discretized ODEs. So you can use like method of lines to generate automatic discretizations, which basically convert your partial differential equation model to a ODE or a linear solve, like how you want it. And I think the last thing, basically in this, like a lot of work has been done in physics for machine learning, and for that we also have a package called Neural PD, which basically allows you to seamlessly integrate a lot of neural networks for solving PDs using pins. And finally, this is the work that I was doing, so I'm gonna also share a demo of that. It's like a lot of how can you leverage parallelism or for GPUs in this case. So diffeq GPU basically provides a very high level interface of like using GPU acceleration in ordinary differential equations, and which is like sometimes may feel counterintuitive because ODEs are serial processes, so it's like sometimes you need to have like particular like use cases where you're simulating a lot of ODEs together, or let's say there is a big ODE and you want to like accelerate all the, let's say, the array-based computations on a GPU or CPU. So diffeq GPU like especially works on a lot of ensemble problems where you're like simulating a lot of small differential equations on a different parameters. So yeah, I'll just show a demo like how basically we're gonna solve these, and like basically the demo is very very composable, that we work from a very high level interface. That essentially what we are trying to say is that you can basically bring all the components together, and you don't don't need to like write a specific API for, let's say, diffeq GPU or stochastic diffeq, something like that. So I have an example set it up here. Maybe I'll just like try to run this if this runs, but yeah, it's already compiled, so you can just see the output of that. So basically, in this case, I'll be using the Torkils model in this, which is like a catalyst model of the equation, and try to basically do a parameter parallel sweeps. So we have this model loaded, and then we basically declare some of the parameters that we have. These like some of the like default parameters we want for the compiling of the model, and then this basically is like a grid, like a mesh of all those points where you basically want the parameters to have. So this model specifically has 6 parameters, so you can see like 6 grid in this case. And now we'll basically just take a Cartesian product in this. So like it will basically like generate 168,000 ODEs, like stochastic differential equations in this case. Simply, this is some of a boilerplate code that, okay, now we basically give a function, so like how a new stochastic differential equation will look like. So it will just basically do a remake on the parameters, and then some initial value declaration in this case. Which is like, I think this is like, 4 states. And then this catalyst model can be automatically passed to an SD problem. You just like basically take this model, like the sigma gen system, to pass on that, and then basically we do a modeling toolkit on that to basically generate a compatible form. But yeah, so I think these are the ingredients which are like necessary to basically like start for GPU acceleration, and then basically you declare an ensemble problem with the problem definition and things like that. And then you basically like simulate this. So I have a comparison here, like the times are already written. I don't want to run it here because it's going to take about a minute, which will like take some time. So 53 seconds like typically take if you do with ensemble thread, which is like the default CPU multi-threading. And then if you basically just automatically change it to like GPUs, it will gonna take like 14 seconds. So if there's like a 4x speed up instantly, and you are just like working from a catalyst model. If you want more fine-grained control, so this is like not the end of the story, because a lot of overheads are like there from basically transferring from CPUs to GPUs. And lastly, there's like something on lower level API, which I wanted to show in this case, which basically get rid of this overhead by not converting to CPUs. And then you basically see that, oh, it's like, it takes like it's pretty fast. It takes, I don't know, it's some microseconds, which is like around 100 times faster. So this is this basically, yeah. So this basically enables all the GPU acceleration that we have. We started from a very high level model and then like easily can be like break up into just GPU acceleration. So I'm now gonna go back to my slides and then talk a bit about, talk a bit about equation solving. So now let's say you know a bit more about the equations that you want to solve, and let's say, okay, you know you need to do linear solve, or you know something about the model. So we do have like very direct APIs to equation solving. So linear solve, like solving AX equal to B systems, directly provides, and which comes with a lot of preconditionals, a lot of extensible like solvers, iterative solver, direct solvers, things like that. And similarly, building on that, we also have like nonlinear solves, which basically just solve the nonlinear equations. And for computing integrals, like using quadrature techniques or like Monte Carlo estimates, there's integrals.jl to basically compute integration. So now I have a demo which basically says that, okay, now how can you basically step upon these features to like get good simulation times for your example. So I'm gonna show one of them.
Maybe skip it.
Okay.
Do you think?
Yeah. So I'll probably go a bit fast. I think the time is not that much, but yeah. So this is a partial differential equation model, which is, I think Tork will cover that, which is written in ModelingToolkit. We provide the differentials, and like this is like the Brustlater PD example, and then we basically write the equations like, okay, these are like the boundary conditions in this case, and then like define the domains, and we basically like now generate a PD system upon that. And this is the discretization level, which grows like n square, so there will be around 1,000 ODs in this case. And then we also like basically go through the discretization technique, which is like the method of like finite difference technique. But now we basically call the discretization to automatically generate good approximation schemes of discretization, and which now creates an OD. And this OD can be like directly simulated to the solver that you just use, and this is completely tuned, can be tuned by your own. And finally, and like coming up onto that, let's say now you have like, you want to use iterative solvers. So you can just like load linear solve and then use like GMRES methods, which is just like an argument to the solver. And let's say you want sparsity detection, like you want to basically do a lot of Jacobians in this case. So it basically now you want to basically sparsify your Jacobians. You can do like use symbolics to use Jacobian sparsity. And now this basically, I think the times are not shown here, but yeah, this basically will iteratively improve your simulation times. And you can also use like factorization. So like that's like the story that how things are being composed. I am not like, these are not part of a single package. These are composed of all different packages. And finally, the last piece that is that, let's say if you want to use precondition, which is like exactly the information that you know about the model, is like you can use incomplete LU in this case by basically providing it, by using the package incomplete LU. And finally, you have a precondition in this case. Like now, the whole story basically is boiled down so that you can step upon these iterations of the solver and like try to find what works best for your models, and you will see a lot of speed-ups, a lot of stability like comes around and like works very seamlessly with the composability that SciML have. Now I'll pass to Vaibhav to basically talk about more high-level APIs.
Okay, so we are running very late. So I'll have to probably skip the examples I was going to show, but it will be there on GitHub, so I'll give you the link. Anyway, so now we move on to, so we were able to see how we can create models and solve them, right? So the next thing is basically model calibration. You want to solve inverse problems. So there's I don't know, there's like at least 3 or 4 different ways you can do that, but the simplest way you can do is you can use diffeq paramestim. What that does is it takes your ODE like whatever differential equation problem you have, and it gives you out an optimization problem, which I will talk about in a second, and you can just it's all automatic. The optimization problem is basically from the optimization.jl package. That's a package that we have developed sort of aiming to create API to different, a wide variety of optimization solvers, including global, gradient-based, I don't know, and maybe even we have support for mixed integer linear programs and So it's the sort of the entry point to all of those solvers in SciML. Yeah, though that's basically done through these wrapper packages that live in the optimization.jl repository in the lib folder if you're interested. But anyway, we have at this point I think more than 20, at least 15 from what I remember. So that gives you access to like almost 100 different optimization solvers. And all you need to do is you need to change the second argument to get access to all of that. Jump, you all know what it is, but it's a DSL. So that can be a bit restrictive for some of these problems that we have. So that's why we had to sort of develop optimization. Automatic differentiation is sort of like the backbone of a lot of these things that we are able to do with these packages. It serves as so we have support for at least these 4 different AD packages at this point. And I think Zygote is missing from that, so like there's a bit more as well. And that enables you to do basically the local sensitivity calculations which live in SciML sensitivity, which is essential for being able to solve these inverse problems. Okay. And then you have data-driven DiffyQ, which is basically to to recover equations from data. So when you have just a data set and you want to, something very similar to what Miles was talking about yesterday, you just want to recover equations from data. This leverages the sparse identification algorithm, if you have heard of it. And then DiffyQ flux, that's like very essential to the SciML story. That's where these that's the interface to being able to use to compose the neural networks from these machine learning libraries like Flux or Lux to be able to create neural ODEs, universal differential equation, deep equilibrium networks, and everything else. DiffyQ base is very similar to DiffyQ parameter system. It's like a very easy interface to solve Bayesian inverse problems. And Turing is the leading probabilistic programming language in Julia, and it's completely composable with the entire SciML stack. So there's a very good tutorial on the Turing tutorials, so you can take a look at that. Easy model analysis was a recently developed package where a lot of these things that I have been talking about so far and will be talking in terms of like global sensitivity analysis or inverse problems, this gives you very convenient APIs to directly use all of that on modeling toolkit models, basically, and sort of uses. It's a completely symbolic interface. Some of these that I've talked about you might have to move out of the symbolic stuff. Yes, global sensitivity analysis for performing global sensitivity analysis. Global sensitivity.jl is for performing global sensitivity analysis, which is basically you're trying to quantify the effect of input parameters on some measure of the output, or even the entire time series of the differential equation if you want. SciML expectation allows you to efficiently compute some moments of the differential equation solves. Structural identifiability is this concept of being able to just use the model structure to infer whether the parameters that you have are going to be something that you can estimate from if you have some data, basically. So basically to deal with overly parameterized models, so it will tell you that, or under parameterized. Bifurcation kit is it's a external package which is for creating these bifurcation diagrams. Dynamical system depends on basically differential equation.jl and provides a nice interface for dealing with agent-based models and such. Plots is plots. Quasi-Monte Carlo, this is useful in cases like global sensitivity or some other place where you have to do some sort of a numerical integration, and this gives you ability to very efficiently generate, and I think also in parallel, very efficiently generate these low discrepancy sequences, which are like supposed to be very good for numerical integration. Surrogates is something. It's the open source equivalent of what Sharan was talking about earlier, but it's like very far behind it. Yeah, it's basically you can create surrogate models for your physical models. Reservoir computing is one of these packages that was developed to support basically eco-state networks and liquid state machines. Cool. I wanted to show a demo, but I don't think we have enough time for it. Oh, why did it not change? But I'll just have to, yeah, I won't be able to run it. But basically, this example, I like this demo quite a lot. What we are doing here is, so this model was special. What happens in this NPZ model, right? The A parameter that you see here, that's actually not identifiable. And it's not identifiable in the sense of structural identifiability. Even the structural identifiability, well, if you run it, it actually tells you it's globally identifiable. But then when you actually run the inverse problem and you try to estimate it with this, even just this, I just used a simulated data set, which should be a very trivial thing, right? Like, but even then you can not recover A basically. So the reason I'm going so much into detail is because this is where the composability comes into play. Now, you can actually run global sensitivity analysis on it, and you'll sort of just see that A has no effect on the output of this model, and that's why you can just parameterize it away. Okay, thank you.
Do you have HDMI? Or? Yeah, I have HDMI. Here, it looks like it's here. Sorry?
You guys ready? So
Yeah.
you just introduce yourselves.
Yeah, sure. Should I introduce us or you want to introduce yourself? Sure. Sure. All right. Hey, everybody. My name is Frederick. I'm here together with Venkatesh Prasad, and we will talk to you about the ModelingToolkit standard library that you are able to use to quickly get out to speed with an MTK model. So just a very brief overview of MTK standard lib. It's a library. It's in the name. It's of reusable components from multiple different domains. And with domain, I mean things like mechanical, thermal, magnetic, hydraulic, and so on, right? It's composable with the SciML ecosystem that comes from just using ModelingToolkit, right? And as of very recently, it's also ready for the graphical user interface. So as a library, it has lots of different sub-libraries, as we see some of them there. Basic blocks are things like PID controller, state space system, low-pass filter, gain, matrix gain, and so on. We have mechanical components, so those would be your masses, springs, joints, gearboxes, all of that. Electrical, you can kind of figure out what's in there, but also a few non-trivial libraries like thermal, magnetic, and also not shown on this slide is hydraulic. So thank you, Brad, if you're here, for providing that. And of course, each of these libraries have a lot of components inside of them. And let's see, yep. When I say a component, we have a screenshot from the graphical user interface here with a kind of the component library part of that. It's things that, like a capacitor, for instance. And what makes it a good component? It's something that has an equation associated with it, and you only have to write that once. And then you can put that capacitor into all of your models and just change the parameter. Maybe you would like to have a more fancy version of a capacitor that also has an internal resistor. Okay, you can make your own fancy capacitor and extend the library that way. So it's very simple to extend. You can extend by implementing new components where you write the equations. If you are the domain expert, you can do that. You can also write components that are composed out of several lower level components. So for instance, if you compose a bunch of capacitors and and resistors, you create perhaps a low-pass filter. So those are different ways you can extend the library. Another nice feature, of course, it uses ModelingToolkit, but with that comes a composability with the rest of the SciML organization. So we had a talk a couple of hours ago on the QR code there for doing control analysis using ModelingToolkit standard library models. You can also do things like structural identification. So here structural identifiability kind of analysis. So here we load a package with that particular name, and we call the function assess local identifiability. And the model we pass in this case is an RC circuit. And it turns out that you can not actually identify R and C separately, because the product of R and C is what we call a time constant. You can identify that. So here we say, can I identify the function or the expression R times C? And it responds with 1, which means yes, you can. All right, cool. So you can use interesting things from SciML like that. I said it's ready for the graphical user interface. Here we show a screenshot of that. There was a video shown on the Julia Hub sponsor talk. We see, maybe I should stand here. We see here a number of components, and the way you kind of put these components together is by connecting these lines, all right? And each such line between these colored blocks is represented in code with a connect statement. So if you write this in code, you would have connect the negative pin of the resistor to the positive pin of the capacitor. That would be one connection, and it's visualized here as a line. And then, of course, this is a simple model, but with this you can build incredibly complicated and complex model. For instance, this could be a car where you have suspension and wheel and motor and all of that stuff, right? And the key point is that you don't want to start modeling a car by writing down the equations. You probably want to start using higher level components that someone else have implemented for you. All right, and with that, I would like to hand over to Venkatesh, who will dive into more detail.
Yeah, hi. So in the gray picture is the old way we wrote the ODE systems in the standard library. So we recently switched to using MTK model macro that MTK provides. So this is more convenient, as you can, is more expressive, and also it provides, it automatically generates a structure which then we can plug into GUI and get the components based on that right out of the box. So I'll go into detail of how this works. You can have your parameters and variables in the parameters and variables block. You have to line separate them, and you can have their default values. These default values are set. If the user has his own default value, what happens is all these parameters and variables are implicitly promoted as keyword arguments. So user can pass his own default value if he wants to change. And then in this example, it's EMF, so it has voltage and current as well, and a positive and a negative pin. In standard library, there is a component called oneport, which already defines them. So we just want to extend them. So we have an extend macro, with which we are specifying that we want to pull out the V and I, voltage and current variables, and we are naming it as oneport. One thing to note that is the variable list has to be a tuple. So if it's just V that you want to pull out, you still have to make it a tuple. And then it uses the extend function of MTK. It's equivalent to that. And then EMF also has 2 more components, that is flange and support, which is from rotational library. Here, if you notice, flange has set a default value to phi. So that's how you specify to the MTK model macro that, okay, this flange dot phi can have a value set by user. So user cannot now pass any value to support, but if he wants to set any default value, he can set to the flange.phi. So for that phi, he can pass the default value. That is a toggle that you can use for passing the default values to the subsystem. And then at equations block has all the equations that are specific to EMF, what makes it EMF module. And if you notice at the end, there is no ODE system. You don't have to define it again. So that is taken care by the macro itself. It sees, okay, these are the parameters, variables, components and equations, and okay, this is the ODE system I need to build. And one convenient thing it does is now you no longer have to specify all the systems it has, and sometimes we miss out one of those, and we build really large models with those, and we get an imbalanced equation. It becomes a debugging nightmare. That's no longer the case. And then you can create EMF component. Either if you're using @named macro, it automatically passes the name, and also you can use a dot. Subcomponents can be accessed via dot. So flange.phi would work. If you are doing it as a normal function, then the notation changes to double underscore. So it would be flange double underscore phi. That's the notation we are following. And you also have to specify the name of that EMF component. And then if you see the next picture, that's the generated structure. So it already knows what components there were and what variables there are, and also the keyword arguments. So K had nothing, no default value, so it is promoted as OK. And then independent variables are also there, and what is extended, parameters and equations. So the advantage of this is now you can just plug this into the GUI, and GUI can define the ports there are and what equations to expect and what values, keyword values the user might provide. So it is very much pluggable. And then I would like to briefly go over how we can stack all these various components that library has into one big model. Here I'm using electrical submodule and rotational submodule and blocks. And then I'm going again with an MTK model macro. In that, I'm defining components, which are from electrical library, the ground, voltage, resistor, inductor, and EMF. And step function is the waveform that we are expecting the source to have for the voltage source, and one more for the torque. So those two are coming from the blocks. And then torque and inertia, damper, all these are from the rotational library. So this continues to the next page. We define how these are connected. If you can see that the flange and the support have internally, they have phi angle and tau torque. And the electrical components, N and P, are the negative and the positive pins. So they have voltage and the current as their variables. So you do connect negative pins and the positive pins and flanges and the supports so that those variables are connected together. In case you miss and connect a electrical pin which has a different set of variables to a flange, then it just gives you an error saying that, okay, these cannot be connected. So you don't have to worry, and all these connectors has an information that, like components can be connected, and you can see that everything here is in the same block, sort of electrical and rotational part is in the same block again, while not causing any problem. And then you just create a system out of it, and you structurally simplify, create a ODE problem, solve it, and plot the value. It all works. Next thing is, as soon as I run the DC motor, it gives you a structure. So even for this, I just plugged in all the components in the library and created a larger model, and it gave you a structure. So this structure can be again used for GUI to have a tile for DC motor itself, so that that just works. And if there is one more set of DC motor, if there are other things, those things can be connected together as well. And no additional work is required. It just works directly. And then this is how the GUI looks. Yeah. 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 So Julia Hub now has a tile for Julia Sim. There you have all these components from standard library, and also HVAC and batteries are also there. So you can use all these to build, drag and drop and build a circuit. And then, yeah, it uses the structure that I showed earlier. And you can also view the code and also get the plots. You can change the timestamp and variables, and all those things can be done. Okay. Yeah. So with this, the future plans, for the DSL, we are also adding if-else conditions, so that currently, if there is an equation saying that, okay, if this particular parameter is false, don't pass these variables, that doesn't work. We will be adding shortly. And subcomponents currently have numerical default values. We want to switch that to symbolic. That is coming as well. And more readable error messages is something we are adding as well. And additional libraries. We want to add noise and discrete blocks, all these libraries. And if you have any libraries of your own, you can add them as well. And the GUI support, we are trying out what works best for various domains. We already have an idea of, okay, if these domains, models are from these domains, then this is how GUI might be more friendly. So if you have your own library, then do add it and try out and give us a feedback on what GUI should look like for your particular library. And if you have any components in mind, then just add to standard library, and directly that will be part of GUI. And special acknowledgements to Brad and Valentin, who contributed some of the submodules of standard library. And yeah, for more on this, for the documentation, you can scan this one. And for standard library, it's the other one. You can try out and create issues, add more models. Yeah.
All right. Any questions? All right, lots of questions. I don't know who was first. Let's start. Yeah. All right. Johnny?
Yeah. So the MPK model macro, can that handle, for example, like if you have certain variables that are actually vectors or something like that, and normally you kind of have to manually scalarize them to create, the different variables. Can that handle vector components like that?
Do you mean the variables or the components?
So like, let's say, so I work with like rigid body dynamics a lot, and you might have a position and velocity as part of your states, and those are like 3-element vectors or something. Usually in ModelingToolkit, like you can't just, you can't just pass in, like you can't just define the 3-element variable as a symbolic thing and put it in, you have to scalarize it.
Yeah, that isn't supported yet, yeah.
So the limitations there are the same as for ModelingToolkit, and the answer is that it's going to require JuliaCon compiler to handle array variables the correct way. Yep. Yeah, Torkel.
So you have a lot of specific packages which feed into ModelingToolkit, and like this more general. Do you have like a good idea or guideline for like when like a new type of domain feature would fit in the ModelingToolkit standard library, and when it should more like fit into a separate package?
It should be reasonably reusable for a wide community, right, to fit in the standard library. Having said that, if you are implementing models for organs in the body or something like that, there is a fairly wide community of people who are interested in those. There is no harm in adding such components to the model library, provided that it provides a fairly comprehensive model library. If it's just a very small part, maybe it's not worth it. Also, it should follow a certain standard in the sense that it should be easy to maintain for the maintainers of the model library, unless you are willing to volunteer for a very long time there.
Please
of course.
volunteer.
Yeah. Please volunteer. But the structure of it's very easily extendable, and it doesn't have to necessarily live in the standard library. It can live in its own package as well. The standard library is as first class as anything else, really. The only thing that is required is that you implement your model using this MTK model macro, so that the structure is automatically there. So in that sense, the standard library can serve as a reference implementation for how you implement those. And if you follow the best practices we try to establish there. The library you provide can live absolutely anywhere, really. Yep.
Yeah, I think the last thing is a point to emphasize, right? So the Modeling Toolkit standard library lives as a reference library for what Modeling Toolkit component libraries should look like, right? So if you ever want to know, like, oh, I want to build my own weird library, you can always look at the Modeling Toolkit standard library as an example, and anything that follows that form is something that's compatible with all sorts of different things, all the downstream Modeling Toolkit stuff, but also the GUIs that are being built and all the things that are like the surrogates and everything. All of this is all compatible with whatever follows that, right? Now, whether something can be in the Modeling Toolkit standard library or in a separate repo, that's more organizational stuff at that point. Modeling Toolkit standard library right now is kind of targeted towards things like you see in the Edelman standard library, though it's not necessarily restricted to that space, right? We just haven't done things beyond that. But we are interested in if someone like says, oh, I have this kind of drive JSON string or something, and if you want to do it. I think that the key thing about it being in Modeling Toolkit standard library rather than a separate repo is that things in SciML have a nice support structure, right? So with SciML, we tend to have the Julia lab and all sorts of people, and all these contributors that'll help keep things alive, right? And so it's like, is this for your own project? Do you want to just play around with it, or is this something that you think is really reusable and you want to make sure it's kept alive, but you also don't want to maintain it yourself, right? That's kind of a place for Toolkit standard library.
There is one, yeah.
Talking about Biochemical and other modeling frameworks, one thing that always comes up in discussions with my collaborators who are clinicians is units. So my units are SI units, and Modeling Toolkit are almost like design units, but many of the models are in physiological units, millimeters Hg for pressures, etc. Is there a scope for including unit form in that whole thing, in that A-course modeling framework, that I can define something with units defined in the components that are then transparently translated to whatever unit comes in?
Units are already allowed in Modeling Toolkit. There's a separate documentation page that describes defining units and things. And it will automatically do unit checks
Yeah.
and unit validations.
Only the checks and validations.
So here with the description, you can also add the units while defining the parameters and variables.
That's
Yeah.
the unit that it expects the parameters.
Yeah, yeah,
So that's basically
yeah.
like a docstring. What I'm thinking about is a bit more so I can connect, for example, something that comes in with a pressure in pascals, but that big component expects the pressure or gives outputs of pressure in millimeters internally. And
Okay.
is that translatable? But in other applications, when I hand code my ODEs, unit for works and it all translates through. But in the A-course modeling framework, I wasn't able to do that.
Yeah. So yeah. Right now, it expects that everything is written in terms of the same unit piece without conversions, right? So what it's able to do is able to validate units. It's able to validate dimensional analysis and say this equation is dimensionally correct and this equation is not dimensionally correct, right? And throw warnings and such. It's not able to then say, oh, if you want this thing to be in this unit and this thing in this unit, well, meters is 1,000 times millimeters, so therefore we should be doing adding 1,000 times multiplication here, right? It does not do that. I would prefer to change things from unitful to dynamic units because I really hate the unitful package and I think it's a bad design and no one should ever use it. But that's something we can talk about later. But yeah, I mean, so
I have no horse in that race, whichever.
yeah. Well, so basically, units are a bit behind because I think that the unit library is not good and we want to change that and then fix units.
But there may be units in the future.
Exactly. But yeah, well, I mean, and Miles Cradler actually put out a new units package, which is a lot better, and so hopefully we'll be building off of that. So we might be changing the unit validation stuff to require that and no longer unitful. That's a whole story that should be going on over the next year. Basically, units are a bit behind because we didn't like the unit package. Now we got some unit packages that we like more, and so now we plan to do it right.
But that's the one thing that is missing compared to the other.
Yeah, for sure.
So So this has different submodules and everything if you see It has single release for all those things. So if you add some components to one of those libraries, it's still entire standard library is released. But yeah, it is structured into sub modules, and those sub modules have a few more modules, and it's like that. Yeah. Yes, yes.
It's a fairly lightweight package. It is essentially
That is
just
true.
symbolic models in there.
That's true. It's just this much.
Yeah, certainly. So
Okay, I need to log in.
the reusability, we are supported by the Julia package manager. So a model has all of the support of a traditional Julia package, right? In terms of reproducibility, that you can instantiate exactly the same thing at a later point as you are using right now.
So
And
this type.
for launching the graphical user
Yeah.
interface. Yeah. So you can access the graphical user interface from the Julia Hub website. You need to log in, create a free account, it's free, and then there is an app under applications that is called Julia Sim. And if you launch that, you should get launched into the graphical user interface. But to continue more on the traceability, a model in the graphical user interface is just a text file, and it's fairly readable, human readable. So that is managed by Git. Well,
So the thing is, you can drag and drop and build your own model, and you can export that. And you know, if there is a model already that can be re-imported, and you can even save, and you can you know, make that one of the other tiles. So sort of, if there was blocks, the DC motor at the end had its own structure, right? So that could be its own tile at the end. So yeah, that can be again connected with something else.
so in theory, when you have saved a model to text, and if you would edit that, we can obviously load a model from disk also. But I don't expect the syntax of that file to be something you would necessarily like to edit. You can obviously do things like change parameters and all these things. That's fairly straightforward. Yeah. But there is some layout code in a language that is essentially not Julia, right? So it's not as nice, at least, to edit. All right, since we have 4 minutes more, I would like to mention one additional thing if you create your own libraries. The ModelingToolkit standard library contains one submodule called blocks. And the block, what makes something a block is that it has an inherent causality. So ModelingToolkit is an acausal language. A resistor doesn't have an input or an output, it just has 2 pins. But the block modules actually do have causality. So they are things like a source. Here is a sinusoidal signal. That only has an output. It's things like an integrator. It integrates the input to provide an integrated output. If you are relying on things, building models that take inputs, try to make use of the components that are called real input and real output, and they're also eventually Boolean and integer inputs and so on, because that would make it fit together with a lot of other tools that rely on this kind of input and output functionality. So that's one thing you could potentially keep in mind. All right, cool. Thanks.
Thank you.
So you can start whenever and you can introduce yourself.
Yep. Do I use this one? Oh, do I use this one or do I use this one, right? Yeah, I'll just use this one. Hey, everybody. So my name is Jeff Varner, and on behalf of my co-workers, so folks from my lab at Cornell and our collaborators at the University of Vermont Medical Center, I'm here to present a package that we developed for building biochemical systems theory models, or BST models, of coagulation dynamics. So the BST model kit package is a lightweight package that transforms a model specification file where we describe the structure of the model into a set of BST differential equations. We're focused on modeling metabolic or signal transduction networks, and it solves these equations using differential equations JL. Okay, so what is a BST model? So if we focus here on this little toy network here, so what we're modeling is the concentration dynamics of the different chemical species in these types of pathways. So for example, if we focus here on metabolite B, let's say, so traditionally we would build a model that looks something like this. We'd write a differential equation around the concentration of B. We would have a set of terms that produced B, and then we would have a set of terms that consumed B, where these R's here, these are the kinetic expressions. So let's say Michaelis-Menten in the case of enzyme catalyzed reactions, or Hill functions, or whatever it happens to be. So biochemical systems theory models, which were developed originally by Savinju starting back in the late 60s when he was a graduate student at Stanford and have progressed through the years, these take a slightly different perspective. So these are power law representations of the net production rate or the net consumption rate. And so you can interconvert between these two representations by essentially log expanding or Taylor expanding the log of these net rate of input or net rate of output. So BST models, there's different representations, and what we're going to talk about today is something called the S-system representation, which is this net power law type representation. They have a really nice mathematical structure. So you have essentially a lumped rate constant that describes the net rate of production of component I, and then a lumped rate constant that describes the net rate of consumption of component I, and then these reaction orders G and H are your nonlinearity in the system. Okay, so how do we go from that equation form to actually building one of these models? So we have different types of model specification formats. So what I show here is just an example of a flat file format. We also take JSON, TOML, and we're working on SBML. But the big idea here is that I have some sort of model representation that's just a file. I load that, I pass that path parameter into a build method, and we get back this BST model type. And that BST model type contains everything that we need in order to simulate the model, in particular the stoichiometric array, so the G, so the reaction order array, and then our rate constant array, in addition to some other initial conditions and so forth. Okay, so the package exports this BST model type. And then it also exports a number of different functions for working with those. For example, evaluate will solve the model, steady state will solve the dynamics of the model. So all it's doing is taking the model type, pulling the data out, making an ODE problem, and calling into differential equations JL. Steady state works in a similar way. And then we've also did this for we've taken the model type, a performance function, and we'll call into global sensitivity. In this case, this is the Morris method. We've also implemented Sobel here. Okay, so this is how we create the model. So I wanted to spend a few minutes here talking about the case study that inspired this, and that's looking at maternal mortality rates. So this was an article actually in March from the Wall Street Journal that talked about how maternal mortality in the US has hit the highest level since 1965, and there are pretty stark racial disparities there. So if we dig down in that data a little bit and just sort of summarize, so in 2018, there were on order 17 maternal deaths per 100,000 live births, and in 2021, there's about 33. Okay, so we've seen on order a doubling of the deaths per 100,000 live births. And this, we've known for a long time that coagulation, the proteome, both the coagulation proteome and the fibrinolytic proteome are significantly altered in pregnancy and often leading to hypercoagulable states, so meaning increased clotting potential. And so this is seen here, pregnant and postpartum women have about a 4 to 5 times higher risk of developing clots compared to non-pregnant women. And between 2017 and 2019, if you just look at this thrombotic embolisms, that's about 8.7% of pregnancy-related deaths have to do with clotting. The other interesting bit here, though, is that hemorrhage has caused about, on order 14% of the deaths can be associated with hemorrhage, which is not a hypercoagulable state, it's a hypocoagulable state. So we have coagulation malfunctions both. They clot too much, or they don't clot enough. And so we have been part of a clinical trial going on at the University of Vermont where we're trying to study this set of biochemical interactions. So in particular, we're looking at the formation of clot here, or fibrin, and how it gets managed. But what I'm going to talk to you today about is actually a little bit upstream of that, and that's how clots get formed, how it gets initiated, and in particular, how we activate this key protease here called thrombin. So this is the output of the coagulation cascade. This has been modeled by many folks, including us in the Vermont group. And these models tend to be pretty large, so they're on order 50 to 100 ODEs. They have a lot of kinetic parameters. So there's a lot of uncertainty associated with this. So we decided to take a different track here. Instead of building these everything in the kitchen sink models, we wanted a low-order biochemical systems theory model, which is only 17 differential equations and only a handful of parameters that we don't know, as a low-order alternative to these traditional kinetic models. And so the question is, okay, well, does it describe the data that we see? Because we're giving up an awful lot in terms of the biological description. So the first thing that we did here is we just stepped back and we just looked at the data. And so our data set here is a population of 37 patients where we have longitudinal data going from before they were pregnant, first trimester, second trimester, third trimester, delivery, so literally right after they delivered, and then 6 months afterwards. And so we have, for each one of these visits, we have 32 clinical features that we are monitoring, so coagulation of fibrinolytic proteome and functional data. So in other words, what we're going to talk about today is something called thrombin generation assays, which is how well do these pregnant patients generate thrombin. And so if you just look at the data itself, we did some synthetic data analysis here as well as looking at the actual patient distributions. So if you look at this plot here, the gray circles that look kind of the smush in the background, this is all of our synthetic population. The open blue circles are our synthetic patient population that we constructed just by computing the covariance and the mean from the data itself, and then the filled-in circles are visit one, our actual visit one patients. Okay, so what we can see is if you just compare V1 to V6, that as the patient moves through the course of pregnancy, they move from the lower left to the upper right, and so that's interesting because this is factor 10 levels. So factor 10 is a precursor to thrombin activation on the horizontal axis, and on this axis is the maximum clot firmness, so how well they clot. So that's interesting. But in addition to looking at the population, we can dig down to individual folks here. I'm just going to focus here on, for example, this panel. So on the horizontal axis, we have time, and on the vertical axis, we have activated thrombin. So this is what a typical thrombin generation profile looks like. So the solid blue here, this would be the actual subject 1 thrombin curve for visit 1, and the orange would be the thrombin curve for the visit 6. And this region around it, this is a synthetic population of patients that we created by sampling in a local region around subject 1. We did this just by using our distribution and then using a kernel method to essentially calculate similarity and throw points away that aren't similar. Okay, so if you just take a look at this, this is subject 1, this is 42, this is 24, and this is all, well, for 12 of the data points. You can see, you can see that, for example, the peak in the orange is higher than the peak in the blue, so you become more coagulable as you become pregnant, and the area under the curve is larger. We can then, of course, interrogate any one of these patients in our 37 real patients or any one of the synthetic patients, and that's shown here in this panel where we did more sensitivity. And so this is V1 and V6, so V1 is basal, not pregnant, V6 is third trimester. And we can figure out what parameters are important not only globally to the overall response, but then we can start to compare V1 to V6 at a patient, individual patient level. So we can, for example, figure out subject 1, what's making subject 1 work versus subject 42, because subject 42 has a particular abnormality which will give them about a 15-fold increase in their likely to miscarry, PCOS. Okay, so what did I talk about today? So we developed this BST model package to study coagulation dynamics. So BST ModelingToolkit JL is a lightweight package that sort of rides above differential equations JL. And it's used to simulate these sort of low-order coagulation models. And we interrogated those models for individual patients in basal as well as third trimester. So I want to thank our funding sources. This work was supported by the NIH. This is the trial here, which is ongoing. We're just finishing up our enrollment. And then this is a R01 that was precursor R01 to the trial. Okay, and I'd be happy to take any questions. Thank you. Chris.
Yeah, so I'm kind of curious that you're targeting differential.jl, but then you said that you're trying to look into doing the SciML reading, right? But is there a reason why you haven't been using the ModelingToolkit interface, especially with the SciMLCon reader?
No. No actual reason. It's just I didn't do it. So it's and that's why I'm interested in what was talked about in the session. I talked to some folks, and so that may be a next step for us. Because I'm just going to say, maintaining, for example, with the flat file parsing and the format, maintaining that parser, huge headache, right? And it's kind of brittle. So to be able to plug into more standardized tools, I think would be a great step for the package.
Was there a discoverability issue? Like, did you not know about it before getting?
Yeah, that was an issue. I mean, this is a fairly, and it was also, I had to get this done before my NIH, investigators meeting, so I just did what I knew how to do. But now that it works and we've shown some proof of concept that it's okay, there are a number of different directions that we're going to go. And one is to make it more usable to other folks, because you can use these types of models in metabolic applications too, and they're quite powerful there. Thank you.
Okay. All right. So my name is Nina Schmidt, and today I want to talk about universal differential equations for parameter estimation in systems biology. This is a joint project with Maren Phillips and Jan Hasenauer from the University of Bonn. So I guess I should, even though you might have heard of this concept already, briefly introduce universal differential equations. The key idea is that we want to combine mechanistic knowledge with some form of universal function approximator. In most cases, we use neural networks. So we describe the dynamics of a state using some components that are known, some mechanistic term, and some neural network. And since quite often we do not directly observe the state that we want to describe, we might also need an observable mapping where, again, we can have some components that are known and some components that are unknown. And to simulate this, we simply pass the dynamic formulation into an ODE solver, get then as possibly hidden state variables that are then possibly mapped with the observable mapping to something that we compare to measurements that we've taken. And then the parameters of both the neural network as well as the mechanistic terms are optimized jointly. Now, in the context of systems biology, UDEs are also applicable, but one has to bear a couple of things in mind. And we started into this project having seen some examples of Lotka-Volterra or easy SIR models, and thought, okay, what happens if we now use a typical problem for systems biology? And what I brought with me today is this problem. It's the boom problem, so it is a real-world problem that has been described fully by mechanistic terms, but we played around a bit with it and analyzed what happens when we delete some of the known components. So what happens if we delete one of the hidden state variables, what happens if we delete one of the interaction terms, what happens if we have missing knowledge for the observables. And this problem consists of 8 state variables, 3 observed states, and as you can see here, it is already a bit more complex than Lotka-Volterra or SIR. So why is this problem representative for lots of systems biology problems? Well, we have nonlinear observable mappings that are quite often also not invertible, like in this case. We have noisy and sparse observations, and we're dealing with a stiff system. And actually, I started this project in Python. The stiff systems part brought me to Julia, actually, because there was no way of solving this using Python. So thanks a lot for what was implemented there. In order to make this work, we could not just use the UDE as I described initially. So we could not just estimate the parameters directly. We needed to do some adaptation to make this work. So one thing that we thought about was including a noise model. Quite trivial when you come from the mechanistic perspective, right? But when you come from the neural network side, it's something that you might not always use, or that's not standard to use. We also included a parameter transform, such that knowledge that we have about parameter constraints can be realized with arbitrary optimizers, that we have some lower and upper bounds for our parameters, which at the same time, if we use a tonnage bound, has the nice property that is actually equivalent to estimating the parameter in log space, which works quite well. We also investigated regularization to support the recovery of hidden dynamics and at the same time prevent overfitting of the neural networks. And something that proved for us to be quite important was also a concept of multi-start optimization. Yeah, I can talk about this topic solely for 15 minutes, so maybe afterwards you can just approach me and we can have a proper chat about this topic. So let's get back to this application. So when we model a partially unknown system with a UDE, in this setting, we replaced one of the state variables that is hidden completely within neural network. And we can see that we can retrieve the observables, that in this setting, the neural network actually even also describes the hidden state variable okay-ish, but that not all of the hidden state variables can be retrieved, which is, however, not a big surprise considering that we have a non-invertible observable mapping in this problem, right? This is an example of what happens if we have insufficient regularization. In this scenario, we use the neural network to model the observable, or one observable mapping, basically. And I mean, now the neural network is in a setting where it more directly influences the output of our model, and hence regularization becomes even more important because the danger of overfitting is more concretely there because we don't have any ODE solver in between that also introduces some kind of regularization. This, I thought, was quite interesting as well. So if we just pick different starting points for a very complex problem, and this is an observable, right? So it should be possible to fit that. We tend to have a problem of ending up in local minima that are really not that good. And so finding good starting points is also quite a crucial topic for UDEs from our experience. In comparison, even though I said before that regularization is important, if we find a good enough starting point, in some scenarios that we looked at, the regularization does not have such a big influence anymore. So, yeah. To sum this up, I think when one works with UDEs, it is super important to keep both perspectives in mind. We are combining mechanistic modeling with neural networks, and when we deal with UDEs, we have to keep both perspectives in mind and remember that when we come from mechanistic models, the ODE parameters have a mechanistic interpretation, and we are interested in the precise values. We are interested in solving a global optimization problem. So the challenge here is the exploration of the parameter space. Whereas if we come from the neural network perspective, the parameters do not matter that much, or the precise values of the parameters. Like any local good enough solution is fine for us, right? So we need to regularize this to prevent overfitting, and this is kind of the challenge of neural networks. So really have to keep those two perspectives in mind and find a good balance between the two. Yeah, and this being said, thank you very much for your attention, and if you have any questions, I'm here until Saturday, so we can discuss it here, or drop me an email. I'm always happy to discuss this further. Chris.
Yeah, so with the plot that you showed, right, that is a classic example where you probably have to use a collocation or method or a multiple shooting in order to fix the fitting there. Did you try either of those as another way instead of just multi-star?
I mean, one problem with multiple shooting is that if we have hidden states and we only know one of the initial values, we would have to estimate all of them as well, which is not always feasible. What was the other idea that you said? We have not looked into this, and we should do that more properly. What we did is, however, we started with a pre-training, with a warm-up training to get to better starting points than just, I don't know, Latin hypercube sampling, for example.
For the multi-start optimization, did you use the interface in optimization.jl, or was it insufficient?
We implemented it ourselves, actually.
Did you complain to Biochemical and tell them that the interface needs to get better?
Okay. Honestly, I just did not look at it, so I can't really complain about anything that I haven't looked at.
You should chat with them on that, because that is one piece of the library you want to improve anyways.
Okay, cool. Yeah, I'll do that.
I have a question for nobody wants to ask a question. Well, I come from geophysics, and we, especially in seismic imaging, we work a lot on regularization. We have different types of regularization. And neural networks, I don't see that thing being very much explored. For instance, if you use one-way regularization, you can improve sparsity, but you can also use a derivative inside the one-hole, and then you improve edge preserving, right? So you can shape the image the way that you want by changing the regularization. So what type of regularization are you using? Have you looked at the different types that they are?
Yeah, so the example that I showed here on the slides is just the basic L2 regularization, but actually at the moment we're investigating different options of regularization.
Did you do some kind of hyperparameter optimization for the
regularization strengths?
For the Lagrange multiplier that you use?
Yeah, sure.
Okay.
Yeah.
How important was it to add the noise model?
So the noise model was one of the first things that we added, so we should probably have another isolated experiments, leaving all of the other things that we've changed, fixed, and like including noise model or not. What I particularly like about a noise model is also that it gives you automatically an estimate about how noisy your data are, so you get an estimate for the aleatoric uncertainty, and I think this is always quite nice to have, no matter what model you build. And at the same time, if you're, like, I guess it depends on the problem, but if your states operate on different scales, then obviously it becomes even more important because the noise model can take care of some of the internal scaling of the different states. So I guess it's problem dependent. Okay, then thank you very much.
Okay, hello everyone. My name is Rajiv Shobit Voletti. I'm a PhD student in aerospace engineering, currently an intern with Julia Hub. I'm going to be talking about Quadrotor trajectory synthesis and control in Julia. So the Quadrotor model derived is using a force balance on a rigid body. The Quadrotor is a differentially flat system. For those new to controls, a differentially flat system is one where the state of the system can be expressed as a function of flat outputs and their derivatives, which for our case is described as the position in space, x, y, z, and the heading psi. We use the position, velocity, rotation matrix, and angular velocity to describe the state of our Quadrotor. The dynamical equations are explicitly defined in MTK. The Quadrotor is a very well documented problem in controls and serves as a platform to showcase controls, estimations, and various other applications. So we assume that the thrust produced by the four rotors acts upwards in the body axis, and the moment caused by them is denoted by m. The assumption aligns with those made in literature, as the individual angular velocities of each rotor can be related to the thrust and the moment through an invertible matrix shown. We assume no constraints on the thrust and moment for now, and the required thrust and moments can be mapped to low-level controls through the invertible matrix. So the control inputs are the thrust required and the moments generated along the three axes. To follow trajectories designed, we use a nonlinear geometric controller. The idea behind this is similar to a backstepping controller, which involves designing desired dynamics for the Quadrotor and stepping back to cancel the nonlinearities and inversely find the control input required to affect the desired dynamics. The advantages of using a nonlinear controller, such as the geometric controller, is that it accounts for the nonlinearity of the system. The state decays to the desired value of the output exponentially, thereby ensuring precise tracking, which is evident from the graphic, which is hard to do with just a linear PID controller. The geometric controller follows the trajectory precisely, whereas the linear PID controller overshoots a little bit. This can be mitigated through gain tuning and heuristics. However, the geometric controller is far easier to deal with in this application. The geometric controller allows us to perform acrobatic maneuvers like the stabilizing of a falling quad or having a Quadrotor track a tight spiral much more effectively than a linear PID would. So the next piece of the puzzle is the trajectory optimizer. The optimizer is multi-segment between n waypoints. The cost to optimize is the snap, or the fourth order derivative of the position, to ensure a smooth trajectory. It uses osqp.jl to solve the resulting optimization problem to generate polynomials in time of the flat output of the differentially flat Quadrotor system. The generated trajectories are smooth, which avoids the wear and malfunction of motors. They can be made more aggressive, like making the quadrotor fit through tight spaces or execute tricky maneuvers that require precision. So the trajectory to be generated can be customized for specific applications, like if smoothness is not a particular concern, the objective can be to minimize the time taken, or the fuel, or the battery consumed. The trajectory generation process can be extended to a wide variety of systems and trajectory synthesis problems. And so this is the overall structure of integrating the trajectory optimizer with the quadrotor using a geometric controller. So based on an array of waypoints and corresponding time required for each segment that needs to be designed, the trajectory optimizer synthesizes a desired output, which the geometric controller uses along with the state feedback to synthesize the control to make the quadrotor follow the desired trajectory. The control generation and trajectory optimization has been done using JuliaSim control, and the quadrotor model is a part of the aerial vehicles model library within JuliaSim. So in this marquee visualization of the simulation, we see the quadrotor following a trajectory generated between 4 waypoints. The first and the fourth waypoints are at the origin, and each segment takes about 1.25 seconds by design. So as you can see, the quadrotor hits all the waypoints and returns back to the origin as planned smoothly. The trajectory optimizer in its current form can be used for path planning, and the geometric controller tracks this optimal trajectory rather well. So yeah. Thank you. Yes.
You mentioned the cost is the fourth derivative, presumably the position, but how does that, I mean, I have two questions really about that. How does it ensure that it's actually going to end up going to waypoints? And second, in many of these kind of cases that I've seen, part of the cost function at least is the transit time for the trajectory.
Yes.
So you neglected the time to actually perform this maneuver?
It's not that I neglected it, it's a design parameter. I can also take into that account and have it do it in minimum time, but the plan here was to make a minimum snap trajectory, which, so if there's like rubble and stuff and the quadrotor has to track a really tight like little corner, it cannot just sort of be janky about it because it might hit one of the rotors onto the side, so it has to be really smooth. And so when you want to ensure a smooth movement through like a really small space or a corridor, you would minimize the snap as a standard, which is like the second derivative of the acceleration. Just so the position, velocity, acceleration, and the jerk are smooth, and it's just going right through. The waypoint is a constraint. Yes, the waypoint is a constraint. But so we have the flat output variables, the state of the system, and so the flat outputs, the trajectory, what the trajectory optimizer is generating is polynomials in time for the flat outputs, which is the x, y, z, and psi. And so the optimizer is not related to the dynamics. It takes into account the waypoints, the time that you need to traverse the waypoints, and it spits out a polynomial in time for the flat outputs to follow, which will make sure that it hits all the waypoints and comes back to the origin in the specified time. Thank you.
one thing or one